Hello everyone, I welcome you all to the amazing platform of Physics Wallah. Today we are here to discuss our new chapter Hydrogen under the one short lecture. So before starting the chapter, I want to tell you that hydrogen is a very easy chapter. You have to just listen all of the important things, start making notes side by side, and what you can do is that most of the things of this chapter is already covered in the other chapters like S block, like redox, like organic, right? So you will get to know that many of the things you are already knowing, like equilibrium also has many of the things which are covered in this chapter. So let's start the chapter hydrogen. So if we want to study the chapter hydrogen, first we should know every of the important detail of hydrogen element. Every of the important detail of the hydrogen element. First of all, hydrogen is considered as the first element. It is considered as the first element of periodic table. First element of periodic table. After that, if you want to know the symbol, the atomic mass, the atomic number, so we can simply say that hydrogen is represented as 1:1, where this respective number which is present downwards is considered as Z, which is the atomic number. This is considered as A, which is considered as atomic mass, right? This is considered as atomic mass, whereas this is considered as atomic number. Atomic mass is equal to number of protons plus number of neutrons, whereas atomic number is only considered as number of protons, right? After that we have that if you talk about number of neutrons, then that is considered as A minus Z. So here if we have the calculation of the number of neutrons, then that will come out to be 0, right? Existence of the dihydrogen. It exists as a diatomic molecule. Hydrogen exists as a diatomic molecule. It is considered as a diatomic molecule, which is H2, as its atomicity is 2. And talking about the isotopes, it has 3 isotopes. We will discuss about the isotopes in the next of the topic, okay? And hydrogen exists as atomic hydrogen. Atomic hydrogen that is considered as highly reactive, at around 5000 Kelvin of temperature. So these are the small important things related to the element which is called as hydrogen. If you want to know the meaning of this word hydrogen, hydro means water, gen means forming. So water forming is the respective meaning of this word hydrogen. Let's move forward. Now we have the isotopes of hydrogen. Now, if you want to know what is the meaning of isotopes, so let's discuss that what is the meaning of hydrogen, which is having the element having the same atomic number but the different mass number. If you can simply say that if I have element A and if I have element B, they have same atomic number but they have different mass number. Their mass number will be different but their atomic number will be same. So they will be considered as isotopes. So they have totally 3 isotopes present with them. One of them is called as protium, other is called as deuterium and other is called as tritium. We will discuss all of these. The chemical properties of all the isotopes of an element are same, okay? So you have to remember that the chemical properties of all the isotopes are same. This can be asked that chemical properties of all the isotopes same, different, maybe same, or any other of the options can be present. So you have to remember this. They have same number of electrons, but due to the difference in their mass number, they have different physical properties. Now the reason can also be asked that why their chemical properties are same. See, whenever you talk about the chemical properties, you're talking about the chemical reaction. Chemical reaction is taking the use of the electrons. So if you have the same number of electrons, your chemical nature will be same. But your appearance, your physical properties can be different, because that physical property depends not only on the electrons, it depends upon the other numbers also, like neutrons numbers, protons numbers. So they have different mass number, that's why they have different physical properties, right? So I'm just underlining the things. Difference in the mass number creates the different physical properties, whereas the same number of electrons, gives you the information that their chemical properties will be same. Okay. Despite having same chemical properties, their reactivity is different. Same chemical properties, but their reactivity is different, because reactivity does not depend on the element itself. It depends upon the its ionization enthalpy, its electron gain enthalpy. So we cannot simply say that it is totally depending upon the only the number of electrons. Okay, so we have to understand that, because the difference in the enthalpy of bond dissociation, right? Because you know that there is a bond between hydrogen, there is a bond between deuterium and deuterium, tritium and tritium. They are not existing as H in the atmosphere. They are existing as H2, D2 or T2. So if you want to talk about their reactivity, first you have to break that bond. So the energy required to break that bond will decide which will be more reactive and which will be less reactive. Fine. So that depends upon the bond dissociation enthalpy, and the order for the bond dissociation enthalpy is like this. So reactivity can differ, that can be not exactly similar to the chemical properties, right? After that there are three isotopes of hydrogen, namely protium, deuterium and tritium. Okay, protium first first of the isotopes we are having over here is protium. First isotope we have over here is protium. Protium, or we can call it as ordinary hydrogen. This can also be asked that what is the ordinary hydrogen? Is it protium, it is deuterium, or it is tritium? So you have to remember protium is called as ordinary hydrogen. Okay. The representation of this will be like this, 1H1. Simply what you call it as hydrogen is considered as protium only. Okay. After that we have the predominant form of hydrogen is ordinary hydrogen. Protium, it has one proton and no neutron in the nucleus, and one electron revolves around the nucleus. Okay. The simple representation of this will be 1H1. You already know there is no number of neutrons present over here, because you know that the atomic number and the atomic mass are same, and I have already told you this thing before. Okay. It is the ordinary form of the hydrogen. Okay. You have to remember this thing. Now we have deuterium over here. Deuterium is represented like this. It is represented as like this. So Z is 1 and atomic mass is 2. So number of neutrons will be 1. Here we have to understand that there is no 0 neutrons. There is 1 neutron present in the deuterium. Deuterium is represented as 2H1, or simply you can write it as D. Both are the same. Okay. It is also known as heavy hydrogen. It is also known as heavy hydrogen. You have to remember this thing, that it is also known as heavy hydrogen. Okay, it is having 1 neutron present and 1 electron revolves. Terrestrial hydrogen contains this much of the deuterium in the form of the H2. This is just a line you need to remember, but it is never asked. But just know that it is the heavy hydrogen. 1 neutron is present, that much is required. Okay. After that we have one more isotope. After that we have one more isotope, that is considered as tritium. That is considered as tritium. One more isotope we have, that is considered as tritium. So tritium is represented as 3H1, or it can be represented as simple T. So the atomic mass of this will be 3, atomic number will be 1, and neutrons will be equal to 2. This is how it is represented. Number of neutrons will be 2. Okay, it is the radioactive isotope. This is considered as the radioactive isotope. It is considered as a radioactive isotope. It emits beta rays. You have to remember all these things. It emits beta rays. Its half life is considered as 12.33 years. What is half-life? Half-life is the time which is required for a substance to become its 50%. Okay, whatever time is required for that 50% completion is considered as the half-life. Okay, so half-life is 12.33 years, and all of these things you need to remember. And one thing more I want to tell you, that its concentration is very less as compared to the protium and deuterium. Its concentration is very less. So these are the points related with the tritium. You need to remember all of these for the deuterium, for tritium, and for the protium. Everything in the isotopes is very, very important. Now we have to understand that the position of hydrogen. Okay, we know that in the periodic table we have discussed, even Mendeleev was not able to identify the correct position of the hydrogen. In the modern periodic table we were not able to identify the correct position of hydrogen, so it's still an anomaly. So position of hydrogen we have to discuss. Position of hydrogen. If we need to discuss, if we want to discuss, what should come into our mind with respect to the position of hydrogen? Let's say if I discuss its resemblance with the alkali metals. First I want to discuss the resemblance. First I want to discuss the resemblance with alkali metals. First we need to discuss the resemblance with alkali metals. So what is happening over here is, see, the hydrogen is having only one electron in the outermost shell, whereas the alkali metals also have only the one electrons in the outermost shell. Hydrogen is having the electronic configuration as 1s1, whereas any other alkali metal is having ns1. So they have similar type of the electronic configuration. Alkali metals and hydrogen have the similar kind of the electronic configuration, and both forms H positive ion. Every of the alkali metal can form +1 charged ion, because after losing that they form stable noble gas configuration, right? Let's say if I have sodium, so sodium is 281 over here. It releases one electron to form 2,8, so it can form a positively charged ion. So I can write over here, both can form positively charged ion. Okay, so this is the resemblance. And even we have one more resemblance, that let's say I take an element from the alkali metals. Let's say I take sodium, so it can form sodium oxide, it can form sodium chloride, whereas it can form sodium sulfide. Similar is the case with the hydrogen. It can form an oxide having very similar behavior to the alkali metals. It can form halide and it can form sulfide. So they show very near to equal behavior with respect to the even reactions also. So you can see both have same kind of electronic configuration, both form same types of the ions, both form same types of the compounds also. So we can discuss that yes, they resemble with the alkali metals. So what are the differences? If there is resemblance, there are differences also. Differences with alkali metals. So what are the differences with alkali metals? What all differences are present? So first difference over here is the ionization enthalpy of lithium. I should not simply say the lithium of hydrogen is not equal to alkali metal, right? So you should know that they are not having the similar behavior in terms of the chemical reactions, because the ionization enthalpy is very different. Okay, so this is the very major difference with the alkali metals. Now if we discuss about the resemblance with the halogens, if we discuss about the resemblance with halogens. Resemblance with halogens. So what will be the answer? Resemblance with halogens. See, if we talk about the electronic configuration, so electronic configuration is simply, we can say, is not similar in the case of the hydrogen and the halogen atom. But one thing which is very resembling is that hydrogen can accept one electron. It is having the electronic configuration as 1s1. If hydrogen accepts one electron, it forms H negative ion. Earlier it was 1s1, now it has become 1s2. So it has achieved the duplet of electron. It has achieved the duplet of electrons, and duplet is considered as stable, okay. Like octet, there is duplet also, both are considered as stable, okay. After that, if hydrogen is like this, let's say I take fluorine, which is 1s2, 2s2, 2p5. So if I accept one electron in fluorine, it becomes F negative. It becomes 1s2, 2s2, 2p6. It becomes 1s2, 2s2 and 2p6. So this is considered as octet of electrons, and that is considered as stable. It is considered as octet of electrons, which is considered as stable. So both of them can accept one electron and can form the compounds, like they can achieve the stable noble gas configuration of the duplet and the octet, okay. After that, we can also say that the ionization enthalpy of halogen is quite similar to hydrogen. The ionization enthalpy of alkali metals was not similar to hydrogen, but for the halogens, they have the same kind of the ionization enthalpy, right? So this is the resemblance. After that we have, we can write over here itself. After that, we can have even one more behavior is similar. That is, both have atomicity. Both have atomicity equal to 2. Even hydrogen exists as H2, and even the fluorine, chlorine, bromine and iodine, all of them exist as X2. So they have their atomicity equal to 2, right? So this is also the similarity between these two. After that, we have differences. Differences. So here we have the difference with the halogen. First of all, hydrogen is having very less reactivity as compared to the halogens. If you are talking in terms of the reactivity, they are very less reactive, right? And electron affinity, the tendency to accept electrons, electron affinity of halogens is very high as compared to the hydrogen. So these are the two differences which are present between the hydrogen and the halogen. That's why there are some resemblance also, there are some differences also. So we are not able to identify the correct position of the hydrogen. So let's move forward. After that, we have the occurrence. First of all, we have to discuss now the compounds of the hydrogen, in which we have to discuss so many of them. First of all, we are having over here is the dihydrogen. So first we have to discuss the occurrence of it. Let's have a look. Dihydrogen is the most abundant element in the universe. It constitutes about 70% of the total mass of the universe. Hydrogen is the principal element in the solar atmosphere. It is present in the outer atmosphere of Sun and other stars of the universe like Jupiter and the Saturn. So this is the simple occurrence of your hydrogen element, right? Now, Like we have the spins of the electrons, similarly we have the spins of the nucleus also in the case of the dihydrogen. So we have to discuss the two spins present for the dihydrogen. One is called as ortho and other is called as the para. What is the difference between the ortho and para spin isomers of the dihydrogen? See, the nuclei of the molecule also have spins like electrons. If the spins of the nuclei of the two hydrogen atoms of H2 molecule are in the same direction, the dihydrogen is called as the ortho. The dihydrogen will be called as the ortho. Ortho, I am simply writing over here that the spin will be having the same direction, and if it is in the opposite direction, it will be called as the para. It is in the opposite direction, so it will be called as the para. So same spin will be the same spin we will be having the ortho, and in the different spins we will be having the para. We will be having the para. So the same spin and the different spins is representing the spin isomers. This is called as the ortho, this is called as the para, and these two together are called as the spin isomers of dihydrogen. Spin isomers of dihydrogen. Spin isomers of dihydrogen, okay, which is H2. Which is H2. Okay. Now, ordinary dihydrogen contains at the normal condition 75% ortho and 25% para. Okay, you have to remember these amounts in the ordinary condition. After that, if we have the very low temperature, around 20 Kelvin, so their ratio changes to 0.018% and 99.82%. Like if we have the very low temperature, then we can simply say that the para forms dominates as compared to the ortho form. At a very low temperature, para forms the major contribution, but at the normal temperature, normal condition, ortho is 75% and the para is 25%, right? You have to remember the ratio, but not always the ratio is being asked. This respective topic is present in your books, but not very much questions are coming from this respective topic. So just understand that these two important points are present. Rest of them, if you want to leave, you can leave. But these are this information, I think you could have a look on this. Okay. After this, we have pure para form can be obtained at very low temperature. As you can see, almost 99% is present the para form, so we can isolate it. So very low temperature, we can have the pure respective form. The physical properties are same for both nuclear spin isomers except their thermal conductivity. Their properties are almost same, but their thermal conductivity is not same. So you have to just remember the 2 points, which are the first 2 points at very low temperature, which is dominating, at the normal conditions, which is dominating. Just these 2 points. I have already ticked the 2 points and you have to remember those only. These are the spin isomers. There is a difference in the spins of the one and the other hydrogen atom. If they have the same spin of the nucleus towards one direction, they are ortho. If in the opposite direction, they are considered as the para. Okay. Let's move forward. Now we have the preparation of the dihydrogen. Dihydrogen can be prepared by the following methods, in which the laboratory preparation method is the first one. In laboratory, dihydrogen is prepared by the reaction of the granulated zinc with the dilute acids, maybe HCl, maybe H2SO4. So you react zinc with the acid, you are getting its salt plus hydrogen gas. Let's say for example, I react zinc with H2SO4. You are going to get over here zinc sulfate plus hydrogen gas. You are going to get over here zinc sulfate plus hydrogen gas. Zinc going from 0 to +2 oxidation state, hydrogen is going from +1 to 0 oxidation state. This is how it is getting formed, this respective hydrogen gas. In this respective reaction, zinc is undergoing oxidation, whereas hydrogen is undergoing the reduction, and this can be decided by the electrochemical series. Why the zinc is getting oxidized, why zinc can reduce the acid into the hydrogen gas. So we need to know all of these things. If I have written copper over here, this can never be possible, right? So you have to remember this thing. And this H2SO4 we have used over here is the dilute one. And one more thing you need to remember is the zinc taken over here is not pure. I should say over here it is not taken as very pure. It is taken as impure. It is taken as impure. Why? Because the reactivity of the pure zinc is very, very less. So we have to make it more reactive by introducing some of the impurities into it. So we have to take zinc in the impure form. Why impure form? Why impure form? Why we have to take the impure form? Why we have to take the impure form? Because we need to remember that, why impure form? Because reactivity of zinc is directly proportional to impurity. Okay, so please remember this thing. This can be asked. Why we need to take the impure form of the zinc? Because the reactivity of zinc is directly proportional to its impurity. So this point you need to understand and you need to keep this in your mind very nicely. After that we can even react this zinc with an alkali to form the dihydrogen. This is the reaction over here. Here we are getting the sodium zincate as the product, and with the release of that we have the hydrogen gas formed. Sodium zincate and the salt of the zinc in the case of the acids, right? Moving forward, during the laboratory preparation, few points you have to consider. Pure zinc you cannot take because the rate of reaction will be affected. I have already told you. During the reaction of zinc, if it is not used the dilute one, if you are using the concentrated this one, so you will not have your hydrogen reduced. I'm again telling you, if you are taking the concentrated one, so your hydrogen will not be reduced. Instead of that, your sulfur will be reduced. Instead of that, your sulfur will be reduced. There will be no change in the oxidation state of the hydrogen. So this is something very, very important to understand. I'm making a star over here that when you are using the dilute sulfuric acid, there is a redox reaction. One is getting oxidized, other is getting reduced. Zinc is getting oxidized, hydrogen is getting reduced. But in this case, this is also a redox reaction, but hydrogen is not having any change in the oxidation state. Instead of the hydrogen, sulfur is getting reduced from +6 to +4 oxidation state. Right? Let's move forward. This point we have already discussed, so you don't need to remember anything over here. Okay. Properties. Now we should discuss about the properties. It is colorless, odorless, tasteless. It is insoluble in water. It is very highly combustible gas. We know all of these things, and these are not very much asked in the examination, but these are the properties and you should know them. Okay. Now chemical properties. The chemical behavior of a molecule is determined mainly by the bond dissociation enthalpy. Dihydrogen is quite stable and dissociates into hydrogen atoms only when heated at 5000 Kelvin. One more thing before this we need to discuss over here is commercial preparation. We need to discuss over here is commercial preparation. What is commercial preparation? This is discussed in the electrochemistry chapter. Electrolysis of water. You do the electrolysis of water, right? What you do? You do the electrolysis of water. Let's say I have water present with us. Whenever you put this into the system of electrolysis, you get two ions present over here. You get what? Two ions. One of them is moving towards the cathode, and here you will be getting the hydrogen gas, and other is moving towards the anode, and there you will be getting the O2 gas. Okay. So during the electrolysis of water, you're getting your hydrogen gas as your product. So you can obtain with the help of this also. In the case of the NaCl, which is aqueous NaCl, brine, there also you can get your respective hydrogen gas. What is brine? Brine is simply NaCl solution which is aqueous. So if it is undergoing the electrolysis, you are going to get Na positive plus Cl negative, and you are going to get H positive plus OH negative. So in the case of the cathode, you will be able to see that Na positive and H positive ions will be moving towards the cathode, and in the case of the anode, Cl negative and OH negative ions will be moving towards the anode. So one is cathode over here, one is anode over here. Now you know that one of the ions will be getting discharged. Either the Na positive or H positive ion will be discharged, either the Cl negative or OH negative ion will be discharged. So in the case of the cathode, which will be discharged? In the case of the cathode, which will be discharged? Which will be discharged? So we will discuss over here. See, the discharge potential. Here we have to discuss the discharge potential that you have discussed in the electrochemistry chapter. Discharge potential over here, which is the reduction potential, is greater for the H positive as compared to the sodium positive. So the cathode will be having the hydrogen gas evolved. Sodium will be present, sodium positive ion will be present in the solution. Whereas in the case of the anode, since the discharge potential of OH negative is greater than Cl negative, but still Cl negative is discharged, because here we discuss the concept of the over potential, that we require very high potential to discharge hydroxide ion as compared to the chloride ion. So even the discharge potential of, or the oxidation potential of hydroxide is more than chloride, but still chloride ion is discharged. Okay, so do not get confused with that. Okay, oxidation potential of chloride is less than hydroxide. Is chloride is less than hydroxide, so it is having the Cl2 gas discharged at the anode. Anode is having only the Cl2 gas discharged, whereas the cathode is having the hydrogen gas discharged. Okay, remember this thing very, very nicely. Which will be discharged, when will be discharged. Please remember the electrolysis of the brine. Now we are discussing about the electrolysis of the aqueous barium hydroxide. This is something very, very important to understand and to implement in your notes, implement in your final readings of the chapter. That is, whenever we are using this barium hydroxide, aqueous barium hydroxide during the electrolysis, we are getting at the cathode hydrogen gas, and this hydrogen gas is 99.9% pure. So purity is considered in this case. They can ask you where in the case you are going to get the purest dihydrogen. So in the case of the electrolysis of the aqueous barium hydroxide, and one more thing you need to remember is, here we use the nickel electrode. Here we are using the nickel electrode. So all of these things you need to remember very, very nicely. All of these things you need to remember very, very nicely, right? Let's move forward. After that, we have these three important points that are required to be considered: water gas, syn gas, synthesis gas. What are all these things? So let's say I have carbon in the form of the coke. So it reacts with water. We have a carbon in the form of a coal. It reacts with water. We have a hydrocarbon that reacts with water. In all these three, we get a product over here, which is CO gas plus H2 gas. This mixture is considered as these names. This mixture is having these three names: water gas, syn gas, or the synthesis gas. Why they are called as synthesis gas or the syn gas? Because this mixture is used to produce a compound which is known as methanol. So synthesis of that, because in the organic reactions we take some of the reactants, we do the synthesis. So sometimes the name can be kept with the respect of that synthesized product. So synthesis gas, syn gas. Okay, so the carbon monoxide mixture plus hydrogen mixture is considered as these names. Okay, if you take coke and if you take coal, whenever you are taking coal, so this respective reaction is given a name. This respective reaction is given a name. The name will be called as coal gasification. The name will be called as coal gasification. The name will be called as coal gasification. And other thing is CO gas plus H2 gas. This mixture CO gas plus H2 gas, this mixture is when passed through 673 Kelvin temperature using the catalyst FeCrO4, and you are going to get the product CO2 gas plus H2 gas. Now, what is happening over here? What is happening over here? That we have to actually do this. See, the mixture of CO and H2 is very hard to separate. It is very hard to separate. So what we do, we react this mixture with the water in the presence of the catalyst FeCrO4 at the temperature 673 Kelvin. As a result, we are getting the mixture over here now, CO2 gas and the H2 gas. CO2 gas and the H2 gas. Now their separation is easy. Their separation over here is easier. Their separation over here is easier. The separation over here is hard. Their separation is hard. Their separation over here is hard. Their separation over here is easier. So you have to remember that why you have to pass all of these things through these conditions. Okay. So 1273 Kelvin temperature, you have to use nickel electrode. 1273 nickel, and here also 1273 Kelvin and nickel as your catalyst. So you are going to get the mixture of the synthesis gas, syngas or the water gas. If you are not able to separate them, pass the mixture through the water. Pass the mixture through the water and you are going to get CO2 gas plus H2 gas, which are easier to separate, right? Let's move forward now. Now we have to discuss all of these things. Okay, so we have discussed that these are the properties of the dihydrogen. They are colorless, odorless, tasteless, highly combustible, insoluble in water. We know all these things. Chemical properties now we have to discuss. Let's say if I talk about hydrogen. Talk about hydrogen. Hydrogen is having the electronic configuration as 1s1. So it can show its chemical behavior in terms of the three domains. It can accept one electron, it can donate one electron, and even it can share that respective electron. So it can donate electron, it can donate its one electron to form H positive, it can accept one electron to form H negative, and it can undergo the sharing of electron to form H2. Okay, so these all three things can be performed for the hydrogen: donation also, acceptance also, and the sharing also. Okay, so you have to remember all of these things: donation, acceptance, and the sharing of electrons. So all of these three things are possible in the case of the hydrogen. Okay, so these three are the domains. This can form the covalent bond, first and second can form the ionic bond. Okay, now we have to discuss, since we are talking about the chemical properties, so first of all you need to know that whenever we have this respective hydrogen gas heated at 5000 Kelvin of temperature, if you are supplying this 5000 Kelvin of temperature, this reaction is highly endothermic. This reaction over here is highly endothermic. You require very high amount of energy to break H2 into two individual hydrogen atoms. Okay, so 5000 Kelvin of temperature, highly endothermic reaction, very endothermic reaction, right? So due to high bond dissociation enthalpy, we are going to get these hydrogens. Now understand one thing is that whenever you break this hydrogen gas into two hydrogen atoms with the temperature being 5000 Kelvin, these two hydrogens are considered as atomic hydrogens. These two hydrogens are considered as atomic hydrogens which are highly reactive, which are considered as very highly reactive. The atomic hydrogens which are formed by this process, that hydrogen gas is hydrogen bond between two hydrogen atom is dissociating with the help of this temperature 5000 Kelvin. You're getting two individual hydrogen atoms. If you have to give this much temperature, whatever is formed is very highly reactive. It is just finding something to get attached with. Okay, atomic hydrogen. Please remember atomic hydrogens. After that, however, I have written all these things already. I have written all of these things, so you know all these things, so don't require to read. If you want to go through, you can go through. Okay, now one more thing I need to tell you over here is one more thing I need to tell you over here is, just a second, that is, wait, now we have one more kind of a hydrogen, that is nascent hydrogen. Like atomic hydrogen, we are also having one more hydrogen which is called as the nascent hydrogen. Now what do you understand by this word which is called as the nascent hydrogen? See, whenever you are undergoing the electrolysis, let's say now only you have discussed with me the electrolysis of aqueous NaCl. Okay, we have discussed this, the electrolysis of aqueous NaCl. Okay, so in that condition, you have NaCl giving the two ions Na positive and Cl negative, and H2O is giving H positive ion and the OH negative ion. Okay, NaCl and the water. This Na positive and H positive is coming at the electrode which is called as cathode, whereas the Cl negative and OH negative is coming at the electrode which is called as the anode. One is cathode and other will be as anode. Now what do you see at the anode? What do you see at the cathode? We have Na positive ion, we have H positive ion. You know that H positive ion will be discharged. I have already told you that these two are going to be reduced. So which will be reduced first will be decided by the reduction potential of these two ions. The reduction potential of H positive is greater than Na positive, so it will be discharged, and that is decided by the electrochemical series which is present in the electrochemistry chapter. Even we study bit of it in the redox chapter. Okay, perfect. Now what is happening? This H positive accepts one electron to first form H, to first form this H. Okay, then this H combines with the other H to form hydrogen gas. Okay, now you know that these two processes are having some names. These two processes are having some name. This is called as the primary process. This is called as the primary process, whereas this is called as the secondary process. One of them is called as the primary process, whereas other is called as the secondary process. And this hydrogen is considered as the nascent hydrogen. This is considered as the nascent hydrogen. This is considered as the nascent hydrogen. Right? Now, the most important thing. The most important thing you need to understand is the reactivity order. Understand is the reactivity order. This question can be asked. This question can be asked, what is the reactivity order of the nascent hydrogen, atomic hydrogen and the molecular hydrogen? So always remember, atomic hydrogen, which was formed when hydrogen was getting dissociated with the help of the 5000 Kelvin of temperature, you were getting two individual hydrogen atoms. Those hydrogen atoms were considered as the atomic hydrogens. Okay, after that we have the nascent hydrogen. After that we had the nascent hydrogen that we have now discussed in the primary process. First we get the H, then 2H combines to give you the H2. Those 2H will be considered as the nascent. They are formed mostly during the electrolysis of any of the compound, if there is the discharge of the H, and sometimes in some of the organic reactions also we get the nascent hydrogen. Like Kolbe electrolysis also we get the nascent hydrogen. Okay, now last is the molecular hydrogen. Last is the molecular hydrogen, which is considered as H2. Molecular hydrogen is considered as H2. This is the least reactive. First you have to break the bond of the HH, you will get the individual hydrogen atoms, then they will react. So it will be the least reactive. So you need to remember the order of these three very, very nicely. Okay, now let's move forward. Now we have the reaction with the halogens. Now we have the reaction with the halogens. Now what is going to happen? See, hydrogen reacts with halogen in a very different manner. There is a different reactivity order and we should see that. First of all, if you see the reaction of hydrogen with the halogens, you are going to get this kind of a product. And I don't think so any of you will have the doubt that how this product is forming. X can be any of the halogens. Now understand, when you are taking fluorine, so the conditions you are using over here is the dark conditions. Even you don't require any sunlight for the occurrence of this reaction. Okay. With chlorine they are using light. Okay. Now chlorine requires light. Chlorine cannot react in the dark. Okay. Bromine requires heating. Bromine requires further some critical conditions, some extra conditions. Okay. Okay. Chlorine. Here we have bromine. And if you talk about the iodine, iodine requires along with the temperature the catalyst also. है ना? This is called as a catalyst. Iodine requires along with the temperature a catalyst also. So they are simply telling you that one of them is requiring no conditions, other is moving towards sunlight, then temperature, then along with the temperature they are requiring catalyst. So the conditions for the reaction is becoming so much critical, so much enhanced. That is, reaction will take place only with the help of those conditions only. So the reactivity order of the reaction is getting decreased. We can simply say over here that reactivity is highest for F2, then for Cl2, then for Br2, and then for I2 in the case of any halogen with the hydrogen. First F2 reacts to give HF very easily. Iodine reacts in the most critical form with the help of the temperature also and with the help of the catalyst also, right? Let's move forward. Reaction with the dioxygen now. No problem, whenever you are having the reaction with the dioxygen, you are going to form the water. Catalyst, or you can simply have the heating also. Reaction is exothermic. You can simply see that the reaction is exothermic. It reacts with dioxygen to form water. This reaction is accompanied with the release of heat, so it is considered as the exothermic reaction. If you want to increase the yield, right? If you want to increase the yield, temperature should be low. As you know that exothermic reactions, are favored by low temperature. Exothermic reactions are favored by low temperature. Okay, whenever you will have the increase of temperature, the equilibrium will shift in the left direction. The reaction backward will be favored. For the exothermic reactions, always you have to decrease the temperature with the help of the Le-Chatelier principle. We can understand this. Okay, so this is the reaction with the dioxygen. Let's move forward. Reaction with the dinitrogen, it's a very important reaction. Let's discuss. If we talk about the reactivity with the nitrogen, dinitrogen, so this process is having a name. Yes, this process is having a name which is known as the Haber's process. And see, in this respective reaction, you are having the nature as exothermic. You already know that this reaction is exothermic in nature. If we talk about the increase in the yield. Sometimes this question is being asked in the P block chapter, that how you can increase the yield for this reaction, increasing the yield for this reaction. See, whenever they are talking about the increase in the yield, that is the simple meaning that they are telling you to tell us that how you can increase the amount of the product. Yield means the amount of the product, right? So for the exothermic reactions, what you can have is, you have to decrease the temperature, and with respect to the pressure, the delta Ng will be 2 minus 3, and that is equal to minus 1. Okay, so delta Ng over here is negative. Whenever delta Ng is negative, whenever you will increase the pressure, your reaction will move in the forward direction. So these are the two conditions which are defined for the greater yield of this ammonia. Okay, now 673 Kelvin temperature we require. 673 Kelvin temperature we require, 200 atm pressure we require. What are the catalysts used in this process? See, you can use your catalyst in the two forms. Catalyst, here you can use the two forms. Iron you can take as a catalyst, and molybdenum you can take as promoter. Molybdenum you can take here as promoter. Iron as catalyst, molybdenum is taken as promoter. What do you understand by the promoter? Promoter increases the efficiency of the catalyst. Okay, and even you can take the mixture of iron oxide plus Al2O3 as catalyst. Okay, so you can have one of this mixture and other of this mixture. These two both are considered the catalyst in the Haber's process. Okay, so please remember these two things during the preparation of ammonia. If you want to increase the yield, you have to decrease the temperature, you have to increase the pressure. Catalyst I have written above, the two mixtures you can use as the catalyst. Okay, with the reaction with metals, now whenever this respective hydrogen reacts with the metals, it forms a number of types of the compounds, and they are simply called as the hydrides. Hydrides. Okay, they have written this name hydrides. You have to remember that reaction with the metal with hydrogen forms the hydride. Okay, now I can underline all these things. I should give a box to you for this. Now, for example, sodium reacts with hydrogen to form a sodium hydride. Calcium reacts with hydrogen to form a calcium hydride. This is having a specific name also, which is called as hydrolith. It is having a specific name which is called as the hydrolith. Okay, now let us discuss the hydrides. Now let us discuss the hydrides. Now let us discuss the hydrides. Hydrides are of the three types. One is called as the ionic hydride, other is called as the covalent hydride, whereas the third one is called as the metallic hydride. Ionic, covalent and the metallic. Ionic, covalent and the metallic hydride. These three types of hydrides we are having. So let's start first the discussion of the ionic hydride. So ionic hydride is the hydride of hydrogen with S block elements, but that M will never be beryllium, it will never be magnesium. Lithium is sometimes also not considered in the hydrides category of the ionic, but this is an anomaly. Sometimes it is written, sometimes it is not written. So we will exclude over here beryllium and magnesium. They are not coming in this category of the ionic hydrides. Hydrogen, if it is combining with beryllium, it will form the covalent hydride. If it is combining with the magnesium, it will be forming the covalent hydride, not the ionic hydride. Remember this thing very, very nicely. Okay, these compounds are stoichiometric. You have heard this word in the solid state chapter. Some of the compounds are stoichiometric, some of the compounds are not stoichiometric. Stoichiometric means, like, if I write over here Fe2O3, it is considered as stoichiometric. If I write over here Fe 0.990, one of the number is fractional. If one of the number is fractional, that is considered as non-stoichiometric. So these compounds are stoichiometric compounds. Like, for example, if you have sodium hydride. you have calcium hydride, right? So they have very high melting points and boiling points. Okay, they are white crystalline solid. They are white crystalline solid. These are the properties which are physical, the crystalline nature, and the white color is the physical property. Very high melting point and boiling points, because the bonding between the metal and hydrogen over here is the ionic bonding, so they will be having a very high melting point and the boiling point. Okay, now we have for the ionic hydride that they are only conducting, they are only conducting in the case of the fused state, or you can simply say the molten state. If the molten state is not present, they are not conducting. Okay, so they are conducting in the fused state. Okay, now if you break any of the hydride of this type, if you provide heat into that, it will become calcium solid plus hydrogen gas. It will break into the calcium solid plus the hydrogen gas. And if you react any of the hydride with water, you are going to get its basic solution plus hydrogen gas evolved. So even you can, with this method also you can prepare the hydrogen gas. Even with this method you can also prepare the hydrogen gas. So please remember all of these points very nicely. All of these points very nicely. And even what else you can do is, yes, if you react lithium hydride with Al2Cl6, you are going to form a very important compound, lithium aluminium hydride. And if you react lithium hydride plus BH3 or B2H6, you are going to form lithium borohydride. Lithium borohydride. If you remember, lithium aluminium hydride and the lithium borohydride, these are considered as very important industrial chemical. They are considered as very important industrial chemical, as they are used as reducing agent, as they are used as reducing agents. They are used as reducing agent. They are very important industrial chemical. They are used as the reducing agent. Okay, so you have to remember that these two are coming under the uses, of this respective ionic hydride. Okay, so please remember they are stoichiometric. They have very high melting and boiling points. They are reacting with S block elements to form the ionic hydride. After that we have, they are white, they are crystalline in nature, they are conducting in the fused state, that is the molten state. If you break them, you are going to get the metal and the hydrogen gas. If you react them with water, you are going to get the basic solution plus the hydrogen gas. I hope this is clear to you. And the uses, they are used in the preparation of this. One more important thing related to the ionic hydride is, whenever you have any of the ionic hydride, if you let it undergo electrolysis, so what will be the product? Electrolysis, what will be the product? Electrolysis, so what will be the product you are going to get? See, sodium will break into the sodium positive and H negative. This will go on the cathode, whereas H negative will move towards the anode, right? And what all products you are going to get? Cathode will have sodium solid as deposited by accepting one electron, and this H negative will release one electron, and two H atoms will combine to form the hydrogen gas. Even you can get hydrogen gas over here also. So you should remember all of these steps. This is primary step, this is secondary step. What hydrogen as alone you are getting is nascent hydrogen, and on the cathode you are going to get the sodium deposited. You are going to get the sodium deposited. So electrolysis of NaH is going to give you sodium and the hydrogen gas. Okay, so all of these are important points regarding the ionic hydrides. Now we have to discuss the covalent hydrides. So covalent hydrides are basically called as the covalent hydride or the molecular hydride. Covalent hydride or the molecular hydrides. These are formed with the p block elements and in the s block elements also, p plus s, and in the s we are only going to take beryllium and magnesium. We are only going to take beryllium and the magnesium. Okay. Molecular hydrides are further classified into the three parts. They are, one of them is electron deficient, one of them is electron precise, and other is electron rich. These are the three categories in which the covalent hydrides are being divided. Electron deficient hydrides, that means they are behaving as the Lewis acids. They are having deficiency of the electron. They are having the deficiency of electrons. Let's say, for example, if I take the hydride of respective group number 13, so you're going to get over here is BH3. If I form the compound BH3, you are going to get this. How many electrons are surrounding boron? There are only 6 electrons surrounding the boron. So it is having the electron deficiency. It is having the electron deficiency. So these are considered as the electron deficient hydrides, and you can simply see this is from the group 13. Sometimes you know that this BH3 converts itself into B2H6, but still it is Lewis acid. You can never say that after becoming B2H6 it has decreased or its electron deficiency is nullified, because that we will study in the banana bonds p block chapter, that nothing is the case happening in the case of the B2H6. BH3 or B2H6, whatever you say, they are always electron deficient. Okay, perfect. Now electron precise. Electron precise means that whatever number of electrons you require, that much electrons you are having. That means you are surrounding by the 8 electrons. Okay. So group 14, any of the hydrides of the group 14 will have the compound as MH4. So you can simply see the structure of MH4 will be like this. There will be 8 electrons surrounding M. There will be 8 electrons surrounding M. If you want, I can draw the 8 electrons. 8 electrons surrounding M. Okay. Now we have the electron rich hydride. Now we have the electron rich hydrides. Electron rich hydrides are the hydrides in which you will have more than, I should not say the more than 8 electrons, but you will have sufficient 8 electrons, but you will have a lone pair, you will have a negative charge that can be donated to some other species which is electron deficient, right? What is happening? You can have a lone pair of electrons, okay, around the electronegative atom. Let's say I have a compound which is ammonia. See, if I make the structure of ammonia, it will be like this. If I make the structure of ammonia, it will be like this, beta. So this is surrounded by, this nitrogen is surrounded by 8 electrons, in which 6 are the electrons plus 1 is the lone pair. So this lone pair, this one lone pair can be donated. This one lone pair can be donated. This one lone pair can be donated. That's why it is considered as the electron rich. So what all groups can form the electron rich hydrides? Your group number 15, 16 and even the 17. All of these 3 groups can form the electron rich hydrides. In the case of 15, you can see ammonia. In the case of 16, you can see water, and in the case of the 17, you can see the HF. Fluorine is having 3 lone pair of electrons. All of these 3 are considered as the electron rich hydrides. Perfect. Let's move forward. If you want to know the geometry, you can calculate with the help of the VSEPR theory. You know all these things. I don't think so that this is something you are not knowing. You can do yourself, right? Now, we have to move towards the metallic hydrides. Now, metallic hydrides or the interstitial hydrides. Now, remember that these are formed by the groups 3, 4, 5, D block and the F block elements, okay? Group number 3, 4, 5 and the F block elements, when they combine with hydrogen, they are forming the metallic hydride or the interstitial hydride, okay? And yes, it is written over here, the groups 7, 8, 9 do not form any kind of hydride. That's why it is considered as this whole three elements are considering as the hydride gap, as they are not forming any hydride gap. They are not forming any hydride, so they come under the category of the hydride gap. Sometimes it is asked that what all groups come under the hydride gap, which do not form any kind of a hydride. So 7, 8, 9, any of the element do not form any of the hydride, okay? In the group 6, only chromium is forming. In the group 6, only chromium is forming the hydride, and that is also the metallic hydride. So 3, 4, 5, all the F block elements. Group 6, only chromium. No 7, 8, 9. 7, 8, 9 do not form any kind of a hydride, either metallic, covalent or ionic. They don't form any kind of a hydride, okay? So remember this thing. These hydrides are known as metallic hydrides because they conduct electricity. Moreover, these hydrides are non-stoichiometric. You can simply see they are non-stoichiometric. You have one number as fractional. You have these number as one of them is fractional. So if you have one of the element in the fractional number, you are considered as non-stoichiometric, okay? So these are the things you need to understand. These hydrides, I have explained this. Please, these 3 points are very, very important. They are asked. This hydride gap is a very famous question. It is asked many times, okay? Let's move forward. Now we are moving towards the next important compounds. First we have discussed the dihydrogen. Then we have discussed the hydrides, the compounds of the hydrogen reacting with the metals. Now we have to move towards the most important compound, which is water. So let's discuss all of the properties of the water. Pure water is colorless, odorless and the tasteless. We know all these things very, very nicely. Water present in the liquid state at room temperature. Water boils at 100 degrees Celsius and changes into the gaseous state, whereas it freezes at 0 degrees Celsius to form ice. We know the freezing point of the water. We know the boiling point of the water because we have studied the chapter solution. There it is mostly used, okay? Water molecules undergo extensive hydrogen bonding. One H2O molecule forms 4 hydrogen bonds, right? They are having the very extensive hydrogen bonding, and you can see, I'll explain you afterwards, okay? The existence of hydrogen bonding is responsible for the high freezing point, boiling point, high value of specific heat, high latent heat of fusion, high latent heat of vaporization in comparison to the H2S and the H2SE. See, this is a group study. So if we are comparing the H2O, H2SE and H2S, water is having high value of all of these properties like latent heat, boiling point, specific heat, because it is having one property associated with it, that is the hydrogen bonding, right? Let's move forward. High heat of vaporization and heat capacity are responsible for the moderation of the climate and temperature of the living beings. Sometimes you know that the temperature is changing for the oceans and for the seas, so the aquatic animals sometimes they feel very difficult to breathe, okay? So that's why if the temperature is very, very high, it becomes very difficult to breathe for the aquatic animals. Like being an excellent solvent, it is essential for the transportation of metabolites in the plants. It's a very excellent solvent. It's a universal solvent. It can dissolve many of the things in itself, okay? Because it is having a very high dielectric constant. If you have a very high dielectric constant, most of the things you can dissolve, but it's not a utmost condition. If a solvent is having a very high dielectric constant, that does not mean that it will be the very good solvent only, because if the solvent is very viscous and if it is having a very high dielectric constant, it is not a good solvent. Viscosity decreases the movement of the ions. If you will dissolve something, the ions will move into the solvent. They will not be able to move freely because of the high viscosity of the solvent. Okay. Now, alcohols, ammonia and carbohydrates dissolve in water due to the formation of the hydrogen bonding. Density of water is maximum at 4 degrees Celsius. That also I will explain you. Now, let's discuss. Gas phase. Whenever you're talking about the gas phase of the water, so there are so many water molecules. It's in the vaporized form, it's in the gaseous form, steam form. So there are so many water molecules. They are not associated there with the help of the hydrogen bonding. They are existing as the individual molecules. Okay. So this is the molecule of water. You can simply see, if you want to know the hybridization, if you want to know the shape of water, we can discuss with the help of the VSEPR theory. So what is happening? Half oxygen 8 valence electron, 2 monovalent atoms, not 8 valence electron, it is having the 6 valence electron and 2 monovalent atoms. So number is coming out to be 4. We know that steric number we have discussed in the VSEPR theory. Please go through the VSEPR theory in the chemical bonding chapter. It is very, very important, and I have explained every of the important case in the VSEPR theory. Okay. Okay. So this number is coming out to be 4. So you have sp3 hybridization. Your geometry will be tetrahedral, and if I talk about the shape, shape will be bent, as you can see over here. These are the lone pairs. What all repulsions are present over here? This repulsion is called as the lone pair repulsion, and this is called as the lone pair bond pair repulsion. That's why it should have a bond angle equal to 109 degree, but it is having 104.5 degree because of the repulsions present. Bond pair repulsion, lone pair repulsion, lone pair repulsion. All of these are giving it the bond angle of 104.5 degree. Okay. Everything is written over here. You are not required to learn any of the bond length. Please remember only the bond angle. No requirement of learning the bond length. Okay. If you want, I can underline this bond angle so you understand that the bond length is not required. Okay. It's not required. This is the orbital picture diagram. If you want to see that how lone pairs are present, lone pair is something diffused electron density. It is nothing very, it is not having any specific position. I cannot draw a dot where the lone pair will be present. It is the diffused electron density which is diffused on the oxygen atoms. So that respective area is coming as lone pair. Okay. Now, the liquid phase, it is having hydrogen bonding. Now let's discuss. If we take a water molecule, let's say this is a water molecule. So, hydrogen bonds it is forming. This is a hydrogen bond. This is a hydrogen bond. This is a hydrogen bond. So, total hydrogen bonds it can form is the 4 hydrogen bond a particular water molecule can make. One water molecule can make 4 hydrogen bonds. You can see simply with the help of the yellow color, it can form the 4 hydrogen bonds. Okay, how they are formed? They are formed like this, that 2 are formed with the help of the hydrogen, 2 are formed with the help of the hydrogens, and 2 are formed with the help of the lone pair of electrons. So total 4 hydrogen bonds a water molecule is making. Okay, you have to remember this thing. In liquid phase, a large number of water molecules are associated with hydrogen bonds with each other. Now the solid phase, which is a structure in the form of the ice. Let's discuss that structure. Ice structure, the structure of ice. Now what is happening over here is, let's discuss. Let's discuss the structure of the ice. What is happening in the structure of ice? Okay, if you see this structure, you can simply understand what is happening. Okay, the angle over here in the structure of ice is 120 degree around. This is the network of so many of the ice, so many of the water molecules. There are so many water molecules present over here. Okay, let's discuss further. As you can see from this molecule, there are this pink water molecule is present in the between. So it will form the hydrogen bonds with this molecule, with this molecule, with this molecule, and with this molecule. So the middle one is forming the hydrogen bonds with 4 water molecules surrounding. Okay, and as you can see, there is a cage forming over here. As you can see, there is a formation of a cage over here. There is a formation of a cage over here. This is a hydrogen bond. Okay, this is a hydrogen bond. I am drawing all of the hydrogen bonds present in the cage. Okay, I am forming all of the hydrogen bonds present in the cage, and I am drawing the water molecules also present. This is a water molecule. This is a water molecule. Again, we have this water molecule. So we have so many water molecules present in the structure of ice, which are forming the hydrogen bonds with the other molecule. With the other molecule. Okay, now what is happening over here? Listen very carefully, listen everyone very carefully, that this respective structure of ice is having one water molecule in the middle, one water molecule in the middle, and rest of the water molecules are present along the sides of this cage. This is known as a cage. This is known as a cage. It is written over here. It is written over here. It is having a cage-like structure. It is having an open cage-like structure in which one water molecule is present in the between and other are surrounding it. Okay, so I am defining some of the hydrogen bonds over here. The middle hydrogen bonds I am writing as A, and the hydrogen bonds present outside I am calling those as B. I am calling those as B. Okay, so there are two types of hydrogen bonds present over here. There are two types of hydrogen bonds present over here, and I'm calling them as hydrogen bonds. There are two types of hydrogen bonds present over here. One is called as A and other is called as B. A is formed, which is present in the between. B is present outside. Now what is happening? This respective structure of ice is present in such a way that these vacant spaces have air trapped between them. These vacant spaces have air trapped between them. Whenever the air is trapped, their volume will increase. When air is trapped, their volume will increase. Okay. Now density is equal to what? Mass upon volume. So in the case of ice, because of its cage-like structure, if volume is increasing, so density will decrease. So density will decrease. That's why the density of the water is more than density of the ice, because its volume is high, because it is having some open spaces, vacant spaces, and that is having the air trapped into them. Okay. Now what is happening? Now the next thing what is happening is, what you do, you move the temperature from 0 degree Celsius to 1 degree Celsius, and then you move towards the 4 degree Celsius. Okay. Now when you move from 0, because ice exists at the 0 degree Celsius, the minimum temperature which is required for the conversion of the liquid into the ice form is the 0 degree Celsius. Okay. So when you are moving from 0 degree Celsius to the 4 degree Celsius temperature, these A bonds starts breaking. These A bonds starts breaking. Okay, when all these A bonds will break, first this whole of the cage will contract. What is happening? What is happening over here? At 4 degrees Celsius, all A bonds breaks. Okay, volume at that time will be lowest because the cage will be contracted. This A bonds will break, the cage will contract. Contract means the volume will be the lowest. At 4 degrees Celsius, the volume will be the lowest one. Okay, it will be the lowest one. So density will be the highest one. That's why we say at 4 degrees Celsius we have density highest, because at the 4 degrees Celsius temperature only all A bonds are breaking. After 4 degrees Celsius, all these B bonds also starts breaking. Molecules starts moving away from each other. All of the water molecules starts moving away from each other. Okay, so you need to remember all of these things. So remember that the density of water is maximum at 4 degrees Celsius. This is the reason. Okay, let's move forward. This is the structure of ice. We need to remember everything in the ice structure. Highest temperature at which the density will be the highest, and all these things. Now let's move forward. That is properties. Now the properties of water. Water is having first of all the amphoteric nature. It is having the amphoteric nature, which tells us that it can behave as a base also and it can behave as a acid also. It is having an amphoteric nature. Now, first of all, we are talking about its nature as a base. Okay, so H2O is reacting with H2S to form H3O positive plus HS negative. Now, this H2O is accepting H positive ion, and this H2S is donating. It is donating H positive ion, and you know that Bronsted acid base concept have a definition that if you are donating H positive ion, you are an acid. If you are accepting H positive ion, you are a base. Okay, so if it is accepting H positive ion, it is behaving as a base. That's why we are calling it as a base. And we are calling it as a acid. Whenever there is a acid, when it is donating the H positive ion, okay, when it is donating the H positive ion, it is written incorrect over here. This is not a base, this is a base. Okay, so what is happening over here, that whenever we have something donating H positive ion, now this is becoming conjugate acid. Now this is becoming conjugate acid, and this is becoming, this H3O positive as a result is becoming this is conjugate base, and this is becoming conjugate acid. Always remember this. Whenever something is base, it is accepting one H positive ion, it is becoming conjugate acid. H2S is having the nature as acid. When it is donating the H positive ion, it will behave as a conjugate base. Always remember these things. Okay, do not forget this. Okay, I should make a clear observation over here that you don't get any confusion. This is the typing error we have over here. Now let's move forward. It can behave as acid also. As it is behaving as a base, it can behave as an acid also. Acid. So what it will do? It will donate the H positive ion. So this will become as OH negative, and then OH negative will be called as, it will be called as conjugate base. And ammonia is a base. It accepts one H positive ion. It is behaving as a base. So here it will behave as a conjugate acid. It will behave as a conjugate acid. It will behave as a conjugate acid. So one of them is conjugate base and other is conjugate acid. Okay. Now we have a very important term which is called as a autoprotolysis. If any of you is having confusion, I should tell you this thing. This is studied in the equilibrium chapter. Acid is a substance. This is a Bronsted concept. This is a Bronsted-Lowry concept. I'm simply writing Bronsted concept. Arrhenius tells us that H positive ion, if something is donating H positive ion, it is considered as acid. If something is donating OH negative ion, it is considered as base. Bronsted said that acid is something which is donating H positive ion. Okay, it is donating H positive ion, whereas base is something which is accepting. Whereas base is something which is accepting H positive ion. Acid, base. You need to remember these two things, acid and the base. Now what is happening? What is this terms? What are these terms? Conjugate acid, conjugate base. Let's say if I say I have CH3 COOH, okay, it dissociates to give CH3COO negative plus H positive. So if this is acid, it will be considered as conjugate base. It will be considered as conjugate base. The other thing which is forming on the product side will be called as a conjugate base. Conjugate base means because it has tendency to accept the H positive ion. It can accept the H positive ion. It can behave as a base. Okay. Now we have over here, let's say ammonia. If ammonia accepts one H positive ion, it is forming ammonium. It is forming ammonium. So this is base. This base is becoming conjugate acid now. This base is becoming conjugate acid now. Why conjugate acid? Because it has tendency to donate H positive ion. It has tendency to release H positive ion. So it can be called as an acid. So from the base you are getting, so it will be called as a conjugate acid. So remember these things. Remember these things very nicely. Remember these things very nicely. This is a reaction. You need to remember it very, very nicely. This is being used in the equilibrium chapter also. Okay. Now let's move forward. Now we have a term over here which is called as the autoprotolysis. That means you're reacting your molecule with its own self. Okay. So autoprotolysis we have over here. Water is reacting with a water molecule only. Okay. Water is reacting with a water molecule only. It is donating one H positive ion. Okay. Okay. Let's have a reaction over here. Example of autoprotolysis. This is water reacting with water to give you H3O positive plus OH negative. Now, one of them is becoming as H3O positive and other is becoming as OH negative. If this is water, if it is accepting H positive ion, so it will behave as a base. It is donating H positive ion, so it is behaving as an acid. So the base will behave as a conjugate acid and this will behave as a conjugate base. Okay. This is base, behave as a conjugate acid. This is acid which is behaving as a conjugate base. So this is autoprotolysis. This is considered as the autoprotolysis. Okay. Now don't look at this, follow this. However, water is neutral towards litmus and it is having the pH 7 that you know, that you have studied from the lower classes also. Now there is also one more molecule which undergoes the autoprotolysis. Even ammonia also undergoes the autoprotolysis. How? We have an ammonia molecule that reacts with the another ammonia molecule to form a reaction which is known as ammonium, and one is other NH2 negative. Okay. Now Now what is happening over here is ammonia is forming ammonium, other ammonia is forming a amide ion. Okay, this is ammonium, this is amide. This is accepting one H positive ion, so it is behaving as a base. It is releasing one H positive ion, so it is behaving as an acid. So base will form a conjugate acid and this will form a conjugate base. Okay, ammonia base is forming conjugate acid and acid is forming the conjugate base. This is the reaction you need to learn, you need to understand very, very nicely. You need to learn, you need to understand very, very nicely. These two are the cases of the autoprotolysis that are considered in the syllabus of our examination. Okay, so please remember all of these things. Now, there are some reactions, some redox reactions which involves water, in which water will, maybe it is oxidizing someone, maybe it is reducing someone, itself it is also getting changed. So what are the redox reactions of the water? Okay, so water, what is happening in this case is water is actually oxidizing the sodium. So here the oxidation of sodium is taking place. So if it is oxidizing the sodium, it is behaving as an oxidizing agent. It is behaving as a oxidizing agent. It is behaving as an oxidizing agent. Whereas in the other case, fluorine is getting reduced. In the other case, fluorine is undergoing the reduction. So with the help of the water, we are able to perform this reduction. So here it is acting as a reducing agent. Here it is acting as a reducing agent. Here it is acting as a reducing agent. So water can act as a both, as an oxidizing agent also and as a reducing agent also. You need to remember, you have to see the reaction. With the help of the reaction, you have to identify that what is the behavior of water in the particular reaction, right? Okay, this is a very important reaction. This is a very important reaction. You know, this reaction can be called as the reduction of the fluorine, and even this reaction is also called as fluorine has ability to oxidize water. Fluorine has the ability to oxidize water. How? Oxygen is having the oxidation state as -2 and here it is having the oxidation state as 0. So water here is getting oxidized. How? H2O is getting converted into O2. -2 is getting converted into 0. So we can simply say fluorine has the ability to oxidize water, and this is very, very important. This can be asked, this can be asked. Please remember it very, very nicely. Okay, even in the above reaction, fluorine with the water, it is acting as a reducing agent as it gets oxidized to O2. It is oxidized to O2 during the photosynthesis also. Okay, during the photosynthesis also, it is oxidized to O2. What they are telling is this. I hope this is clear to everyone. I hope this is clear to everyone. Let's move forward. Hydrolysis reaction. Now understand that what is happening in the case of hydrolysis. Let's discuss what is happening in the case of the hydrolysis. Whenever you perform the reaction of hydrolysis, what is happening? Whenever you have a reaction of hydrolysis, what is happening? Hydrolysis is something when you dissociate water into the H positive and the OH negative ion, and then the reaction occurs. The respective compound which will undergo hydrolysis will also break into the positive and negative ions, and water will also break into the positive and the negative ions as a result. Okay. Now, hydrolysis reaction. Water hydrolyzes oxides, halides to the respective acids. Okay. Now P4O10. Oxidation of the phosphorus over here is +5. And in the H3PO4 also the oxidation state of phosphorus is +5. Hydrolysis, always remember during the hydrolysis, water behaves as H positive and OH negative. Oxidation state does not change. Most of the time, oxidation state does not change. Like phosphorus in the P4O10 has oxidation state as +5. In the H3PO4 also it is having +5. If somebody is not knowing why P4O10 is having oxidation state as +5, they should know this structure, which is being taught in the P block chapter. If you are not knowing the structure of P4O10, you should know this structure, where the oxidation state of the phosphorus is +5. The oxidation state of the phosphorus is +5. So P4O10 structure you should know for the oxidation state. Okay. Now SiCl4, the silicon is having oxidation state over here as +4. So how this SiO2 is formed? It is not the very direct reaction. First of all, you have SiCl4. You react this with the water. It breaks into silicon +4 and Cl minus. This breaks into H positive and OH negative. Now the negative combines with the positive, positive combines with the negative to first give you SiOH4, which breaks into SiO2, because you know that central atom cannot keep 4 OH ions towards not 4 OH species attached to them. So they break, they release water molecule. See, you will be having the structure like this. SiOH4. I'm not making the perfect tetrahedral. I'm not making the perfect tetrahedral. So here 2 water molecules will be removed. Here 2 water molecules will be removed, and as a result you are going to get the SiO2. Okay, this is the mechanism in which this reaction is happening. So SiO2 still has the oxidation state as the +4. So I'm telling you, see, the negative ion combines with the positive ion. Cl negative will combine with the H positive ion. So you are going to get the HCl over here. Now SO3 is having the oxidation state as +6. You are going to get the sulfuric acid oxidation state will be +6 over here. Now even the water hydrolyzes oxides over here and the halides over here. It also oxidizes carbides and hydrides and the nitrides and the phosphides. So even the hydrolysis of all of these compounds are also possible. Calcium carbide we have. See, what is calcium carbide? This is C2 positive plus C2 negative. The ion will be C2 negative. This is called as ethynide ion. This is called as what? Ethynide ion. This is called as ethynide ion. I am writing this over here. There we are not having the space. Calcium +2, C2 negative, which is C triple bond C negative, and this is called as ethynide ion. This is called as ethynide ion, C2 negative. Whenever you are going the hydrolysis, okay, water will be giving you H positive and the OH negative. Water is going to give you the H positive and the OH negative, and this is going to give you calcium +2 and the ethynide ion. Negative positive will combine, calcium will combine with the OH negative, C2 negative ion will combine with the H positive to give you the ethine, to give you acetylene, to give you ethine. Okay, this is acetylene, or you can simply call it as ethine or whatever you want to say. Okay, now calcium hydride also we are having. There is no problem. Calcium hydride breaks into calcium +2 and H negative. This breaks into what? H positive and OH negative. Negative combines with the positive and the positive combines with the negative to form calcium hydroxide and the H2 gas as the product. Okay, now aluminium nitride we are having. Now this is calcium carbide, this is calcium hydride. Now we have aluminium nitride. Aluminium nitride we have. So aluminium nitride breaks into aluminium +3 and N3 negative ions. So positive combines with the negative, negative combines with the positive to give you aluminium hydroxide plus ammonia present over here. Same undergoes with the calcium phosphide. Even the same is undergoing in the calcium phosphide reaction. Calcium +2 plus P3 minus will be given out as a result. N3 negative ion and phosphide ion. This is nitride ion. This is called as nitride ion. This is called as phosphide ion. Nitride ion we have, phosphide ion we have, and you need to remember these very, very nicely. You need to remember these very, very nicely. The carbide, the hydride, the nitride and the phosphide. So hydrolysis of all of these compounds is taking place with the help of the water. Hydrolysis is something in which water breaks itself into H positive and the OH negative ion. The respective compound which is undergoing hydrolysis breaks itself into the positive and negative part. They interchange, they undergo the double displacement reaction, positive, negative, and you get the product as a result. Okay. Now, next we have is hydrates formation. See, whenever we talk about the hydrates, formation with the water reaction, so the identity of the water is not changed. Water is simply present in the form of the entity as water only. It is not dissociated into either of the H positive and the OH negative ion. It is not dissociated, okay? It is same. Compounds like what all hydrates are present around us, that we need to discuss. Where do we find the hydrates? Where exactly hydrates are present, right? So compounds in which water molecules are coordinated. You have studied the chapter coordination compounds. I know you have got the one short lecture of the coordination compounds also. So there totally we have the coordination chemistry in which we have these kinds of molecules present with us. So the water has not lost its identity. It is present in the form of the hydrate. It is present in the form of the hydrate. Okay. Now we have in some compounds water molecules. In some compounds, water molecules occupies the interstitial site. See, there is some ionic compound, there is a lattice point, there is an interstitial point. So, water molecules are present in that interstitial point. So, one of the example over here is the BaCl2.2H2, and you will remember this. You don't need to forget this. Okay. Now we have a compound which is known as the CuSO4.5H2. Now I am explaining you a very important thing in this molecule, copper sulfate dot 5H2. Okay. So how many water molecules in this are attached with the help of the coordinate bond, and how many of them are attached with the help of the hydrogen bond? So first of all, I am making you the possible hydrogen bonds. This is considered as a coordinate bond. So 4 water molecules are attached with the help of the coordinate bond, while rest of them are attached with the help of the hydrogen bond. So many questions are being asked on this respective molecule. So let's discuss over here. So I'm writing over here 4 water molecules. 4 water molecules are attached with dative bond. Dative bond is something when you have an arrow, and I have made that with the green color. So 4 water molecules are attached with the coordinate bond or the dative bond. Okay, 4 water molecules, and 1 water molecule is attached with the help of the hydrogen bond, and 1 water molecule is attached with the help of the hydrogen bond. Okay, you can see this respective water molecule is attached. This is attached with hydrogen bond. Okay, this is attached with the hydrogen bonds, and these 4 are attached with the help of the coordinate bond. They are attached with the help of the coordinate bond. Okay, what all types of the bonds are present in this molecule? There is a presence of the ionic bond, there is a presence of a covalent bond. Okay, you can simply see whenever there is a salt, copper sulfate, CuSO4, there is a ionic bond. Sulfate itself, in the sulfate molecule, there are oxygen sharing electrons with the sulfur. It is a covalent bond. Also, you have a dative bond present over here. And even one more bond is present over here, which is considered as the hydrogen bond. So all of the 4 types of bonds are present in this molecule. This question is being asked, always asked in this respective chapter, that in the structure of copper sulfate dot 5H2, how many are dative bonds, how many are covalent bond, how many are ionic bonds, and what type of bonds are present. So you need to remember it. Okay. Now let's move forward. After water, we have important molecule with us which is termed as hydrogen peroxide, which is termed as hydrogen peroxide, which is termed as hydrogen peroxide. Now we will discuss every of the important thing related with the hydrogen peroxide. First of all, if I ask you the formula of hydrogen peroxide, which is considered as H2O2. Peroxide, what is the meaning of the peroxide? We have this respective molecule which is having a bond which is known as, this respective bond is known as a peroxy bond. Any molecule which is having this peroxy bond has the name ending with peroxide. Sodium peroxide, we have beryllium peroxide. That's why we have the hydrogen peroxide, because of this linkage. This molecule has non-polar bonds also, and plus polar bonds also. This molecule contains every type of a bond, a polar bond also and a non-polar bond also. Let's say for example, if I have this, okay, so this bond is considered as having electronegativity as equal to non-zero. So this bond will be considered as polar. Whereas this bond is having electronegativity difference as 0. So this bond will be considered as non-polar. This bond will be considered as non-polar. One of the bond will be considered as polar and other will be considered as non-polar bond. Okay. After that, in this structure, we can also say that it has a structure looking like a open book like. It is an open book like structure. If I make, it will be like this. This is the structure of respective hydrogen peroxide. It is like open book like structure. A book is opened like this. A book is opened like this, like this. So open book like structure, okay. This molecule is having the open book like structure. Okay. Now let's move forward. The H2O2 molecule, if I ask you, can behave both as an oxidizing agent and a reducing agent. It can behave both as oxidizing agent plus reducing agent. It can behave as both as oxidizing agent also and the reducing agent also. How it can behave like both? So whenever you see the H2O2, it dissociates to give you H2O plus O2 molecule. It dissociates to give you H2O plus O2 molecules. And if I put this respective in a reaction, let's see the oxidation states. Here we are having -2. Here we are having -1. So it is moving from -1 to -2. Here it is undergoing the oxidation, whereas here it is undergoing the reduction. So it itself can undergo oxidation also, itself can undergo reduction also. It can oxidize someone else, it can reduce someone else. Okay. So whenever it is behaving as an oxidizing agent, it will reduce itself. Whenever it is behaving as a reducing agent, it will oxidize itself. So we will discuss that later, but first I am telling you that it behaves as both. Okay. Talking about the H2O2, H2O2 behaves as a bleach also. So since its bleaching action is due to oxidation, so that action will be considered as permanent. Whenever the bleaching action is due to oxidation, it is considered as permanent. Like for example, if I break H2O2 during the bleaching action, it breaks into H2O plus the nascent oxygen. The O2 first we get, that breaks to give you the nascent oxygen. So this is the bleaching action. For this nascent oxygen, it decolorizes a substance. What do you understand by a bleach? Decolorizing a substance. So you are behaving as a bleach. So the bleaching action is due to this oxygen, nascent oxygen, and that action will be considered as the permanent action. That action will be considered as the permanent action. So it behaves as a bleach, it behaves in the form of the bleaching action. Okay, let's move forward. Next, other important thing we need to understand for the H2O2 is this. H2O2 is having, it is a viscous liquid. It is a viscous liquid. Okay, it is having higher viscosity even than water. If you talk about the viscosity, H2O2 is having higher viscosity than water. What could be the reason responsible for that? See, why this H2O2 is having higher viscosity than water? So that reason responsible for it is hydrogen bonding. Greater the number of hydrogen bond, greater the number of hydrogen bond, greater is the viscosity, greater the number of hydrogen bond, greater is the viscosity. If I talk about the hydrogen bonds of the water, so you will say that ma'am, hydrogen bonds forming with the water will be 4. One through this lone pair, one through this lone pair, one this hydrogen and the other this hydrogen. The total number of hydrogen bonds it can form is total 4 hydrogen bonds it can form. If I talk you about the H2O2, what number of hydrogen bonds it can form? It can form how many number of hydrogen bonds? According to you, the hydrogen bonds should be one from this hydrogen, hydrogen, these oxygens and these oxygen. So if I count, there are total 6 hydrogen bonds present in the case of the H2O2. So that's why its viscosity is greater than water. Its viscosity is greater than water. Now, other important thing which is related with this H2O2 is that during its appearance, it has blue tinge in the form of layers. Whenever you will see the H2O2 liquid, you will have a very viscous layers present and there will be slight appearance of a bluish color, that is known as the bluish tinge. So this is the appearance of H2O2. You need to remember this. Okay. Now moving forward, let's write over here only. Now moving forward, there is a problem, associated with H2O2. That is, there is a problem associated with H2O2. That is its storage problem. There is a storage problem associated with H2O2. What is the problem? We have a storage problem associated with the H2O2. Storage problem associated with the H2O2. What is that problem? The problem is H2O2 dissociates. H2O2 dissociates into H2O plus O2. It dissociates into H2O2. It dissociates into H2O plus O2. Right. What are the reasons? In which conditions it will dissociate? It will dissociate in the presence of dust, in the presence of a glass, in the presence of a light, in the presence of an impurity. All of these things are responsible for the dissociation of H2O2. That's why it is kept in dark colored wax lined containers. Whenever you will go to your lab, you will see that always H2O2 is kept inside the lab. Inside the lab there is a room in which it is placed always in the very back of that respective column in which the chemicals are kept. So that's the reason is it should not come in the contact with the light or the dust or anything, because it will be of no use. It will dissociate into the H2O and O2 in the presence of light. So we have the dark colored containers, it's like very dark brown colored containers, right? And it should be of the wax. It should not be of the glass. In the presence of the glass also it breaks. Okay, so you have to remember that it is having the problem associated with its storage also. Okay, let's move forward. Now let's discuss another thing. 1 minute of the water break we are taking. Okay. Now, another thing which is now we have to understand is the preparation of hydrogen peroxide. Now we have to discuss the preparation. Now we have to discuss the preparation of the hydrogen peroxide. Now we have to discuss the preparation of the hydrogen peroxide. Now what is happening over here? First of all, what we have to take? We have to first of all take the barium peroxide. First we have to take the barium peroxide and we have to react that with H2SO4. And this should be cold and this should be dilute. We have to take cold and dilute solution of the H2SO4. Okay, react these two. You are going to get first your H2O2, your desired compound, and then you are going to get barium sulfate, and then you are going to get water. So what is the desired product? Is your H2O2. First method is with the help of the barium peroxide. Okay, this is barium peroxide. It is barium peroxide. It is barium peroxide. Okay, this is barium peroxide. Ba2 positive plus O2, 2 negative ions they are forming. Okay, so its reaction with H2SO4 will give you the H2O2. Another reaction is that it is formed with the electrolysis of 50% solution of H2SO4. 50% solution of H2SO4. Now we have this method. 50% solution of H2SO4 electrolysis can also give you hydrogen peroxide, can also give you the hydrogen peroxide. Now what is going to happen over here? Now understand that whenever we have H2SO4, it breaks to give you 2H positive plus SO4 2 negative. You have electrodes, you have solution dissolved, you have an electrolyte H2SO4. Whenever you pass the electricity, you switch on your respective battery, you get the electrolyte dissociated into H positive ion and the sulfate ion. So they will move towards their respective electrodes. It will move towards the cathode and this will move towards the anode. Cathode will have H positive reacting, accepting 2 electrons to give you what? The hydrogen gas. The cathode will have the evolution of the hydrogen gas. What about the anode? On anodes you have the sulfate which will convert into S2O8 2 negative ion. This sulfate will convert into peroxide. Not peroxide, I should write. It will convert into peroxo disulfate ion. Peroxo disulfate ion. It will convert into peroxo disulfate ion. The structure of SO4 2 negative is like this. The structure of SO4 2 negative will be like this, and S2O8 2 negative structure will be like this. The structure of the S2O8 2 negative will be like this. Here the oxidation state over here will be -2 and -2, and here it will be -1 and -1. So that is happening, that oxidation is taking place. Okay, you are having the increase in the oxidation states. Okay, so you are getting peroxo disulfate ion over here. Now what is happening over here is at anode you are able to see that you are having S2O8 2 negative ion present, but you know that your solution is also containing H positive ion. So this ion will not be present alone. Okay, it will combine with H positive. This ion will combine with H positive to give you H2S2O8. It will combine to give you H2S2O8. This is called as Marshall's acid. This is also called as Marshall's acid. Okay, you need to remember this very nicely. Now we have to undergo the hydrolysis of this acid. Now we have to undergo the hydrolysis of this acid. This electrolysis is not still complete. This will react with water. This will react with water. This will break to give you first H positive over here, OH negative over here. So the product will be HOS, double bond here, and OH over here, and HO, and then O over here, and the rest molecule will be same. So what all things you are going to get? You are going to get this H2SO4, and you are going to get this H2SO5, and this is also called as Carose acid. This is also called as Carose acid. This Carose acid again will undergo the hydrolysis. It will again undergo the hydrolysis. How it will undergo the hydrolysis? Now this is going to be broken up. Here you will get OH, and here you will get the H positive ion. Okay, now the products will be this respective part, this left part over here. OH combines to give you H2O2, and here you are going to get OH plus S double bond O, OH over here. So the products you are going to get is H2O2 plus H2SO4. So finally you have got with the electrolysis your desired product. So you have on the surface of the cathode, you will get your hydrogen gas. On the surface of the anode, you are going to get the Marshall's acid. Then we will undergo the hydrolysis of the Marshall's acid. We will get Carose acid, and the hydrolysis of the Carose acid will give you your desired product as H2O2. So these are the two methods, very important methods for the preparation of the H2O2. Now let's move forward. Other important thing associated with the H2O2. Other important thing associated with the H2O2 is its N factor. H2O2 actually breaks to give you H2O plus O2. It breaks to give you H2O plus O2. Now what all processes are undergoing in this reaction? What all processes are undergoing in this reaction? -2 oxidation state, not -2. Why I am always writing -2, then -2, and then 0. So here it is undergoing the reduction, whereas here it is undergoing the oxidation. So I can simply say that my O-1 is getting converted into O-2 plus O0. So we can simply write this reaction as, disproportionation. We can simply write this reaction as disproportionation. We can simply write this reaction as disproportionation reaction. So we need to know the N factor of H2O2 also. So how do you calculate the N factor? See, first of all, you have to take the oxidation process in which the H2O2 is getting converted into O2. Okay, -1 to 0. Now, how many oxygen atoms are there? 2. How many oxygen atoms are there? 2. What is the charge over here? That will be -1 into 2. It will be -2. So if you are taking out the N factor, how do you calculate the N factor? Oxidation state of the products minus oxidation state of the reactant. Oxidation state of product is 0, and for the reactant it is -2, so it is coming out to be 2. So the N factor for the oxidation process, is 2. So we will simply write N oxidation N factor will be 2. You have to calculate the individual N factor first, right? Now, if you talk about the reduction process, H2O2 is getting converted into H2O, where -1 is getting converted into the -2 oxidation state. Okay. Now, what is happening over here? If we talk about the number of atoms, they are not same. Here it is 2, here it is 0. So you have to multiply 2 over here to calculate, to make both of the oxygen at both of the sides equal. So here you will have the charge -1 into 2 as -2. Here you will have -2 into 4 as -2 into 2 as -4. So what will be the N factor? It will be -4 minus -2 coming out to be -2. So N reduction will be 2. So the N factor for the N reduction will be 2. So overall, how do you calculate the N factor? N factor will be NO into NR upon NO plus NR. This will be the formula for the calculation of the N factor. Okay. So 2 into 2 divided by 2 plus 2, it is coming out to be 1. So 1 mole of H2O2 when dissociates to give H2O plus O2, what are the number of electrons exchanged? Are 1. So N factor is 1 for H2O2. Do not forget this thing. 1 mole of H2O2 have its N factor equal to 1. I hope this is clear to everyone. This is something very, very important and it is being asked. NO into NR upon NO, NO plus NR. Okay. Let's move forward now. Now the other thing associated with the H2O2 is its redox reaction. Now we have to discuss how this H2O2 is behaving as an oxidizing agent or as a reducing agent. Okay, let's discuss that. See, this respective H2O2 can behave as a oxidizing agent, and it can even behave as a reducing agent. It can behave as an oxidizing agent and it can even behave as a reducing agent. Now, how it is behaving as an oxidizing agent, first we have to write in the terms of the reactions. If it is behaving as an oxidizing agent, it has to reduce itself. So the reaction will be this much. And when it is behaving as a reducing agent, it is reducing someone else, so it will oxidize itself. So what will be the case? H2O2 will be converted into O2. Now we have to balance these two reactions in the acidic medium and in the basic medium. Acidic medium, that is the presence of the H positive ion. So what will be the case? The case will be H2O2 is getting converted into H2O. Okay. Now the oxidation state will be -1 to -2. Okay. Are the number of oxygen atoms same? No. You have to multiply a number over here, that is 2. The total charge over here is -1 into 2, which is equal to -2. -2 into 2, which is equal to -4. So here the charge is -2, here the charge is -4. So what you have to do actually, you have to add over here the 2 electrons. You have to add over here the 2 electrons. So the charge now will be same. But what about the number of hydrogen atoms? There are 4 hydrogen atoms over here. So you have to add 2 H positive over here. Now you are going to get this overall reaction, that is H2O2 plus 2 electrons plus 2 H positive is going to give you 2 water molecules as your reaction, behaving as H2O2 as an oxidizing agent in the medium which is acidic. Okay. Similarly, we have the same reaction in the basic medium, or you can simply write the alkaline medium, in the presence of the OH negative ion. So start balancing the reaction. We have H2O2 over here, which is giving us H2O. So what you have to do? Multiply here 2, it is -2, it is -1, and you will have 2 electrons over here. Now calculate the total charge. Here it is having -2 charge. Here there is no charge present. There is no charge. Water is neutral, H2O2 itself is neutral. So if you have 2 electrons over here, you have to add 2 OH negative over here to balance the charge which is created into the reaction because of the presence of the 2 electrons. Now how many hydrogens are there over here? 1, 2, 4 over here and 2 over here. So 6 hydrogens are present over here. And here there are 2. So we have to add 4 hydrogens over here. So we have to add over here plus 2 water molecules. And we have to check either our reaction is balanced or not. How many hydrogens are there? 4, 2, 6. 2 and 4, 6. Oxygen 1, 2, 3, 4. 1, 2, 3, 4. Reaction is balanced. Nothing else we need to do. So the overall reaction will be H2O2 plus 2 electron, and one thing we can do is we can calculate, or we can cancel the 2 H2O molecules to give us the desired reactions, Now what you can do is you can cancel these water molecules with each other and you will get the respective reaction. Okay, This is how you have to balance in the acidic medium and you have to balance in the basic medium. What I'm doing in the basic medium is simply, first I'm calculating the oxidation state. Here it is -1, so charge will be -2. Here it is -2, so charge will be -4. So I'm adding 2 electrons over there to balance the oxidation state charges. So if I have added 2 electrons over here, there will be -2 charge I have extra created. So I have to add over here 2 OH negative to give -2 charge over the right hand side also. But I have disturbed the number of hydrogens, so I have to equalize the number of hydrogens with the help of the water. So I have added water molecules to make the number of hydrogens equal both of the sides. Okay. Now let's move forward. In the reducing agent, how it is going to behave in the reducing agent process. So first of all, we have here also the acidic medium where we have the presence of the H positive ions. So start balancing the reactions. What you are going to get over here? What you are going to get over here? Let's take the same color only. H2O2 is first converting into O2. So start balancing. This is -1 charge over here, this is 0. Both of sides the number of oxygen atoms is same. So -1 into 2. So -2 charges here, there is 0. So add 2 electrons over here. Add 2 electrons over here. The oxidation state is balanced. Now here are 2 hydrogens. There are no hydrogens over here. So just add 2 H positive ions. Your reaction is already balanced and it is very easy to balance. You don't need to write it again. Okay. And what about the basic medium? What about the basic medium where we have to take the OH negative ions? So this H2O2 is getting converted into O2 in the basic medium. This is -1, this is 0. Add 2 electrons over here. You have created -2 charge over here with the help of the electron. So you have to add over here the 2 OH minus ions. Now how many hydrogens are present over here? 2 and 2, 4. So you have to add 2 H2O molecules over here. How many hydrogens? 1, 2, 3, 4. Here also we are having the 4 hydrogens. How many oxygens are there? 1, 2, 3, 4. How many oxygens are there? 1, 2, 3, 4. Your reaction is already balanced. Nothing else you need to do. H2O2 is giving you O2, not H2O2 is giving you O2. We have to add something more also. H2O2 plus 2 OH negative gives you O2 plus 2 H2O plus 2 electrons. So this is how you have to do. Reducing agent and the oxidizing agent. So you can understand that your H2O2 can behave as any of it. Like for example, if I tell you to balance a reaction, it is given that H2O2 reacts with MnO4 negative. What is going to be the product in the acidic medium? You are not even given the products also. So what you will do now? This is the question. This much is the question. So what you have to do? First you should know that H2O2 whenever reacts with MnO4 negative in the acidic medium. So you should always know that H2O2 can behave as both. It can behaves as oxidizing agent. It can behave as reducing agent. But what about MnO4 negative? It can only behave as an oxidizing agent. So this is oxidizing agent present over here. So it has to behave as a reducing agent because MnO4 negative cannot behave as a reducing agent. Okay. So MnO4 negative will oxidize H2O2 into O2 and itself it will be converted into Mn plus 2. First of all, knowing the products is very, very important. Now start balancing. In the acidic medium, if you have H2O2 converted into O2, what will be the balancing? You already know. This is -1, this is 0. Add 2 electrons over here and add 2 H positive over here. Reaction is balanced. Now what about your reaction in the case of the MnO4 negative? That will be MnO4 negative is reacting to give Mn plus 2. Oxidation state over here is +7. It is +2. Add 5 electrons over here. Add 4 H2O over here and add 8 H positive over here. So overall reactions, both of them are balanced. The overall reactions, both of them are balanced. Okay, this will be called as the oxidation half cell. This will be called as the oxidation half cell, because you discuss all of these things in the redox chapter. You discuss all of these things in the redox chapter. You know all of these things, and this is considered as reduction half cell, oxidation half cell, and can be called as reduction half cell. Okay, RHC and OHC. Now you have to see what all electrons are used over here. Here we have 5 electrons, here we have 2 electrons. So we have to multiply this whole equation with the 5, we have to multiply this whole equation with the 2, and then we will add, and then our final product will be as present. So 5H2O2 plus 16H positive plus 2 MnO4 negative and plus 10 electrons. Product will be 5O2 plus 5 2s are 10 electrons plus 5 into 2H positive, that is 10H positive, plus 2Mn plus 2 and plus 2 4s are 8H2. 2 4s are 8H2. You have to keep this thing in your mind that if you are not able to cancel your electrons, your reaction is not balanced. So we are able to cancel our electrons, so our reaction is balanced. So this is how you have to solve the reaction which is present with the H2O2 being either the oxidizing agent or the reducing agent. Okay, so let's discuss the further things of H2O2. Now one more thing is the volume strength of H2O2. Many times this question is asked, what is the volume strength of H2O2, and so many students are confused in this respective topic. So let's discuss volume strength of the H2O2. Volume strength of H2O2. Volume strength of H2O2. Volume strength of H2O2. See, now what is happening in this case? Now what is going to happen in this case, in the case of the volume strength of H2O2? See, what is happening? What is happening over here? Whenever you see that H2O2 is breaking, you see that the products we are getting is H2O plus O2. First of all, you should always know the products formed with the H2O2 breakage. Okay, let's discuss now. H2O2 breaks to give H2O plus half O2 if I write the desired balanced reaction. Now understand very nicely that 1 mole of H2O2 is going to give you 22.4 divided by 2 liter of O2. 1 mole of H2O2 is going to give you 22.4 divided by 2 liter of O2, right? And we can also say that 11.2 liter of O2. See, this calculation we are doing at STP, even it is mentioned or not, you have to consider this at STP. Remember that, okay? Just don't have a confusion in your mind that, ma'am, why if it's not written STP, how we can have the stoichiometric coefficient used as 22.4 liter in the case of the O2, okay? We have to consider this at STP, right? Now, 11.2 liters of O2 are, I can simply say, produced from 1 mole of H2O2. Are produced from 1 mole of H2O2. Okay. So if I write 1 liter of O2, that will be from 1 by 11.2 mole of H2O2. And if I write V liter of O2, it will be from V by 11.2 mole of H2O2. So here first I am going to get the mole of H2O2. We are going to get the mole of H2O2. So if I want to calculate the molarity, that is number of moles divided by volume of solution in liter, we are taking over here, we are always taking over here the 1 liter of H2O2 as our solution. Always we are taking the 1 liter of H2O2 as our solution. So molarity over here will be number of moles divided by 1. And what are the number of moles? It is V divided by 11.2 divided by 1. So it will be V by 11.2 M as mole per liter. So we have calculated over here, the molarity. So you know the molarity. Now you can calculate the normality also. What is normality? Normality is the molarity into n factor. So you will have over here V by 11.2 into 2 as your normality. Here we only consider the n factor of either oxidation or reduction. We don't take the whole n factor over here. Remember it very nicely, okay? Now we have the strength. That is molarity into molecular weight. Molarity is V by 11.2 and the molecular weight is 34. So you can calculate the strength also. And if you want to calculate the percentage strength, that will be equal to S by 10. That will be equal to S divided by 10. So everything I have written over here, every formula I have written over here, you have to just only remember these formulas. That how you are getting towards the mole. What I have done? I have taken 1 mole of H2O2. I am getting 22.4 divided by 2 liter of O2. This is only because of the stoichiometry I am getting. You know how stoichiometric coefficients are related through the chapter mole concept. Okay. Now what we are getting? 11.2 liter of O2. If I divide this, I am just turning back the reaction. Now I am writing this over here. So I can write that 11.2 liter of O2 are produced from 1 mole of H2O2. And I can write if 11.2 are produced from 1 mole, so 1 liter will be produced by 1 by 11.2. Just unitary method I am using. And then I have taken some amount, maybe V liter, X liter I can take anything. So I have taken V liter of O2. So I will get V by 11.2 mole of H2O2. Molarity if I want to have. First I need the moles. I have calculated the moles of H2O2. Molarity, I have the solution volume as 1 liter. Always it is taken as 1 liter. So molarity will be same as moles. Normality is what? Molarity into n factor. N factor I have told you have to take only either the oxidation n factor or the reduction n factor. We are taking it as 2. Strength is considered as molarity into molecular weight. So molarity over here is given to you. Molecular weight you can calculate as 34. Okay, O2 is 32 and then take is 2s for H2, 34. Now strength is S by 10. Okay, this is something very important. Almost everyone is having the doubt in this topic, which is called as the volume strength. Now let's have a question. Calculate the strength of 30 volume strength of H2O2. Now, so many people are confused in the language of this question. Calculate the strength of 30 volume strength of H2O2. Now, what do you understand by all of these things? First of all, whenever it is written 30 volume strength of H2O2, whenever it is written 30 volume strength of H2O2, it means that, it signifies that 1 mole of H2O2 actually gives you 30 liter of O2. That means this is the value of V. So 30 liter is the value of V present over here. Now you need to calculate the strength. So strength, you have molarity into molecular weight, which is M into 34. So molarity was 11, V by 11.2 into 34. So it is 30 by 11.2 into 34. Calculate your strength. You will get, what is the unit of molarity? It is moles per liter. And what is the unit of molar mass? That is gram per mole. So you will get your unit as gram per liter for the strength. Okay. Now calculate the answer. I am also calculating. Now calculate the answer, everyone. What is the answer going to get? We are going to get over here 30 divided by 11.2 into 34. So it is coming out to be 91 gram per liter. 91.04 we are getting. So 91.04 gram per liter. So easily you are able to solve this question, but just you have to remember the formula. Just you have to remember the formula. You have to understand the meaning of the lines. You have to understand the meaning of these lines, that what the lines are telling you to understand. Okay, what they are saying, you need to understand. If they are asking you to calculate the percentage strength, you know that percentage strength is S divided by 10. So make it, these are tricks. Do not consider that ma'am percentage is having multiplied by the 100. No, this is the formula of the ma'am. You have to calculate according to what ma'am have explained to you. Okay. Okay. So I think we have completed the H2O2. I think I have discussed everything in H2O2. I'm just not explaining you the diagrams in the gas phase and that liquid phase of H2O2, that you do yourself. That is totally learning portion. That is open book like structure. There is some difference in the data of the gas and the liquid structure that you can have yourself. Whatever explanation part was present in the H2O2, I have explained. Now we will discuss the heavy water. So let's start. After H2O2, the important compound we have to discuss over here, is our heavy water. The important compound we have to discuss over here is our heavy water. Now understand the case of the heavy water. You know that heavy water is your D2O. So first of all, only the preparation is asked and the uses is asked for the D2O. So focus on these 2 points. Okay. First of all, preparation. So when we discuss the preparation of D2O, what we do is, whenever we see the electrolysis of water, what is happening is, very slight amount of D2O is always associated with water. Like H2O also contains this mixture, this respective mixture also always contains water plus trace amount of, very small amount of trace, or very small amount of D2O. So whenever you perform the electrolysis, it is performed for H2O, and you get as a result H2 gas, you get as a result O2 gas, and the solution present is concentrated with the D2O, because D2O is not electrolyzed. Solution now contains actually the D2. The solution is now concentrated with the D2O. So first of all, with the electrolysis of water, we get in the solution the D2O. Okay. After that, we have the uses of this compound. After that, we have the uses of this respective compound. Okay. Uses. So what all uses are there? It is used as a moderator. You know what is the work of the moderator? First, we have to understand the work of the moderator, because D2 here behave as a moderator. The work of the moderator is to slow down the speed of neutrons, to slow down the speed of neutrons. The work of the moderator. First, you should know the work of the moderator. It is behaving as a moderator in which processes? In the nuclear fission processes. In the nuclear fission processes, it is used as to slow down the speed of the fast moving neutrons, to slow down the speed of the fast moving neutrons. And even you can use this compound in the reactions also. Like you have a reaction CaC2 reacts with water. So can I react this with D2O? We have done the hydrolysis reaction. We will get the same compound CaOD whole twice plus C2D2. Here we are getting C2D2. There we were getting acetylene. Only in the presence of H I have written the D part. Nothing else I have done. You can even do for the aluminium carbide, which is reacting with the D2O, to give you aluminium OD whole thrice plus CD4. I should tell you how the aluminium breaks 4Al plus 3 plus C3 4 negative. Okay, you can have your 3 CD4 and it breaks as Ca2 positive plus C2 2 negative. So you should know what all products you are going to get. You should know what all products you are going to get during the reaction. Okay, CaC2 plus D2O, aluminium carbide plus D2O, calcium OD whole twice, aluminium OD whole thrice, with the C2D2 as one of the product and CD4 as the other product. Okay, so remember this thing very, very nicely. Now we are done with the heavy water. Now we have to move towards the next important part, which is the hardness of water. Many questions are coming from this chapter under the topic hardness of water. Now we have to discuss the last topic of this chapter, which is the hardness of the water. Now we have to discuss the last topic of this chapter, which is the hardness of the water. Now let's discuss that what all ions are responsible for the hardness of water and what type of hardness are present. Okay, hardness of water is responsible because of the ions, which is calcium plus 2 and magnesium plus 2, and their compounds as chlorides, as sulfates, and as the bicarbonate. If you ever see calcium chloride, calcium sulfate or a calcium bicarbonate, it is responsible for the water being hard. If you have the magnesium chloride, magnesium sulfate and the magnesium bicarbonate, it is responsible for the hardness of water. Okay, so the salts, I should not write over here the ions only, I should write over here what all salts are responsible for the hardness of the water, for the hardness of the water, all these three. And if you want to know that hardness, what all type of hardness are there, what all types of hardness are there, okay, so you should know that hardness is of the two types. One of them is considered as temporary, which can be removed, normally it can be removed, temporary hardness, and other is the permanent hardness, that is requiring some very different measures. It is requiring some different measures by which we have to remove the hardness. Obviously some tricky methods we have to use for the removal of the temporary and the not temporary, the permanent hardness. Temporary hardness is because of the calcium and magnesium bicarbonate. Calcium and magnesium bicarbonate. Here we have calcium and magnesium salts of chlorides and the sulfates. Okay, here we have only for the bicarbonates, here we have for the chlorides and the sulfates. Here we have for the bicarbonates, here we will have the chlorides and sulfates of the calcium and the magnesium. So first of all, hardness is due to these ions, hardness is of these types, temporary and the permanent. Okay, now what is happening? How do you get to know that your water is hard? How do you get to know that your water is hard? Let's say I take a soap, I'm bathing, okay, I'm taking a soap which is very hard. I'm taking a soap, let's say sodium stearate, sodium palmitate, any of the soap I am taking. Okay, so let's say I take C17 H35 COO negative Na positive, a very famous soap, we take it as sodium stearate, right? Now I see that when this water is reacting with this soap, okay, I expect that there should be the formation of a leather. Normally, I should be having the formation of this leather. My alarm is starting. There should be a formation of a leather. Jhag we say in Hindi, we call it as a jhag. Whenever you see that washing machine is running, there is a jhag present on the surface of the washing machine. You're putting clothes, you're putting the surf, you're putting your water, and then something is above. That is the jhag. Okay, that is the leather. Sometimes when you are going for the bathing in the bathroom, so there is a I don't know what we call it as. I'm just calling it as a nala in Hindi. So on the nala, the exit points of the unwanted substances we have, okay, the pit point we can say, where we see something is present which is not leather. Something is sticked on that respective exit point. It is not leather. It is something called as scum. It is something called as scum. Okay, that scum is what? That scum is actually, if you take the water, if you dissolve this with water, there is a calcium salt and then is a magnesium salt of chloride, sulfate and the bicarbonates. Okay, so what is happening over here is you are going to get this respective substance which is called as scum. You are going to get this substance which is called as scum, which is not leather. Okay, so what is happening? This scum starts depositing on your boilers. Your laundry is not proper. Okay, you're washing clothes but they are not coming out to be very clean, because you know, if you want to clean your cloth, what you will do, you want to form the leather, you will add water, you will add the soap. Okay, this scum will be formed. Okay, then again you add the soap, again scum will be formed. Okay, when all of the calcium and magnesium ions will be combined with the soap, okay, a large number of this respective compound is formed. After some times, when the the ion present in the water, which is the calcium and magnesium ion, when all of these ions will be combining with the soap, whatever water is left, it will be considered as a soft water. When all of the calcium and magnesium ions present in the water will combine with the soap, your water will be free of these two ions, then you will be having the soft water. But what you are doing in this respective work, it's okay that you're getting the water as soft, but as a result, you are wasting so much of the soap. Okay, you are adding soap. That soap will combine with the calcium and magnesium ion to form this product. Okay, what our work is to break the calcium and magnesium salts. If you break the ion, if you break the salt into the ion, you will have your water as the soft water. Okay, so calcium or magnesium ions will combine with this respective soap and this substances come. This scum will be removed, this scum will be removed, this scum will be removed. Your whole of the calcium and magnesium ions will move out. Your whatever water is left now is the pure one, but you have wasted a very large amount of the soap. So it is not suitable. This hard water is not suitable for the laundry purpose, for the boiling. See, whenever you have your sink in which you wash your utensils, always there is something white deposited over there. That is a hard water. The taps, something white is depositing on the surface of the taps. It is hard water. You have when I was very small in age, we were not having any geyser or something rod kind of a substance to warm our water. So we were using a patila. I don't know what we call it in English. A very big container in which we put water. We put it on the gas. Okay, and it is formed in 10 to 15 minutes. That was used for the bathing purpose. After some time, that respective container develops a layer on its surface. That is the white. Or something whitish kind of a grayish kind of a layer. That layer is of the hard water. It gets deposited on the surface of the boiler, so it becomes something like it is not suitable for the use. Then that layer first has to be removed for the efficient boiling. Okay, so the water has to be first removed from these ions for the better processing in every of the matter associated with the water. Okay, so let's discuss. Okay, now this has come hard water. We should write over here that this hard water, we should write over here that this hard water is not suitable for laundry. This hard water is not suitable for laundry purpose, is not suitable for the laundry purpose, and it affects boilers by making a layer on its surface, by making a layer on its surface, by making a layer on its surface. Okay, now let's move forward. Now we have to understand that how we can perform the removal. We have to remove these hardness. We have to remove these hardness. How we can remove the hardness? First of all, we have to discuss the removal of hardness. First of all, we have to discuss the removal of hardness which is temporary, because temporary hardness is easy to remove. That can be removed in some two type of processes. First of all, what you can do is you can simply perform the boiling. Just simply boil the water. Sometimes you see that the water can be free from the unwanted ions with the help of the simple boiling also. You boil it 2 to 3 times, you are free from the unwanted ions. So what you're doing at that respective stage is you are actually breaking your calcium compound with a bicarbonate which is responsible for the temporary hardness to give you calcium carbonate plus H2O. Okay. And whenever you have a magnesium hydrogen carbonate, you are getting over here magnesium hydroxide plus H2O plus CO2. Okay, so these are the products you are getting when you have the calcium bicarbonate and the magnesium bicarbonate breaking due to the process called as boiling. After that, we can have a method which is called as the Clark's method. After that, we have a method which is called as the Clark's method. Okay, the reagent used in the Clark's method is the calcium hydroxide. So what is happening over here is this calcium hydroxide is reacting with the water present calcium bicarbonate, and it is reacting with the magnesium bicarbonate. It is reacting with these ions, and what product it is producing? Here it is producing calcium carbonate plus water, and here it is producing magnesium hydroxide plus calcium carbonate plus water. So you are free from the compound which is calcium hydrogen carbonate and the magnesium hydrogen carbonate. So these are the two methods by which you can remove the temporary hardness and the permanent hardness. Okay, just go through these two, then we will have the removal of the temporary hardness. Till then I am having the water break. Let's start the rest part. So with the help of the boiling and with the help of the Clark's method, you can produce the desired products. Okay. Now what we are going to have over here is the removal of the permanent hardness. Now we have to remove the permanent hardness. Now we have to remove the permanent hardness. Now we have to remove the permanent hardness. Now permanent hardness can be removed by many of the methods. First of all, what method we can use? We can use the washing soda over here. We can use the washing soda over here. Now washing soda, what is it is doing? Let's say I have calcium sulfate. You react that with the washing soda. It will give you the double displacement reaction to give you calcium carbonate plus sodium sulfate, and you are free from the calcium chloride or sulfate ions that is responsible for the making your water as hard. Okay. Now you can also have magnesium chloride, react that with the sodium carbonate, that is your washing soda, and you are going to get magnesium carbonate plus NaCl. You are going to get magnesium carbonate plus NaCl. Okay, these two types of reactions are possible with the case of the washing soda. Now we can also have another method which is known as the Callaghan method. Now we are having the method which is called as the Callaghan method. First we were using the washing soda. Now we have the Callaghan method. First they will ask you, now what is the Callaghan? Callaghan is Na6P6O18, which is called as sodium hexametaphosphate. Sodium hexametaphosphate. First of all, the Callaghan method. What is the formula for the Callaghan? What is the name of the Callaghan? Sodium hexametaphosphate. Now, how it actually reacts? This Na6P6O18 first breaks to give 2Na positive plus P Na4P6O18 2 negative. First we are going to get this ion. Now what will happen? M plus 2 ion, which is the calcium plus 2 ion or the magnesium plus 2 ion, which is present in the hard water, will react with this anion, which is Na4P6O18 2 negative. Now another 2 sodium ions will be replaced with this M plus 2. Okay, now we will have M Na2P6O18 2 minus, and then again 2 Na positive will be removed. What you are getting from this is, what you have done in this process is, you have removed the calcium and magnesium ion from the salt calcium sulfate or calcium carbonate, and you have attached that ion into the Callaghan. So now this Callaghan part will be taking the calcium magnesium ion. This will be removed through the water, and you will be getting as a result your water as the pure one. Okay, you have to just break the salt which is responsible for the hardness of water, and then as a result you will get your pure water. Okay, so this is the Callaghan method. You have to remember the name. What is the name of the Callaghan? What is Callaghan? What is the formula? How you are reacting? So you need to remember every of the thing. Okay, now let's move towards the next method in the removal of the permanent hardness. Now let's move towards the further methods for the removal of the permanent hardness. Now the third method which we can use for the removal of the permanent hardness is, we can have a zeolite method. We can use a zeolite also. We can also use a zeolite for the removal of the permanent hardness of the water. What we take sodium aluminium silicate. Okay, we take Na as positive, aluminium is +3, and this is SiO4 4 negative. So the charge is balanced. Total positive charge is +4, total negative charge is -4. Okay, so we call it as NaZ. Okay, we take it as NaZ. So what happens? The calcium or the magnesium ions, we call it as M. It reacts with this NaZ in the water and forms a compound MZ2, and Na positive is removed out. Okay, this respective compound contains the calcium and the magnesium ion. So the calcium and magnesium salts, maybe chloride and maybe sulfates, have been broken up, and you are getting this attached with the zeolite. So you have broken your salt which was responsible for the hardness. Even what you can do, you can reuse this. React this MZ2 with Na positive ion or any of the salt of the Na positive ion. You are going to get this M plus 2 replace with the NaZ. You can reuse this. You can even reuse this. So this is a zeolite method for the removal of the permanent hardness of the water. You have to remember this thing, that this is called as sodium aluminium silicate. It will be considered as NaZ. What are the ions? What is the charge? All of these things you have to remember. Now, even you can use this synthetic resin method, which is considered to be the most superior one. Synthetic resin method. This is considered to be the superior one. This method is considered to be the most superior method, synthetic resin method. Now what happens is, here we have two types of exchange resins. Okay, first we have over here is a cation exchange resin. We have over here the cation exchange resin we have over here, and also we have over here the anion exchange resin. Cation exchange resin we have over here, and the anion exchange resin we have over here. What happens? You add the hard water. The hard water contains the cations such as calcium plus 2 and the magnesium plus 2. You have this compound RCOOH. It reacts with the M plus 2 ion, which is calcium or magnesium. You get a compound RCOO whole twice with the M with the removal of 2 H positive ions. Okay. Now this solution passes through a medium to the anion exchange resin. So what all ions are moving towards the anion exchange resin? The ions will be moving H positive, the chloride ion and the sulfate ions, because all of these three are not involved in the reaction. They are present as ions only. The compound of the calcium and magnesium salt is breaking into the calcium plus 2 ion and the chloride ion, magnesium plus 2 ion, or the chloride or the sulfate ion. Okay, so understand that now we have to react with the anion exchange resin. RNH3 positive and the OH negative now reacts with either the chloride or the sulfate to give you actually RNH3 NH3 positive. It is going to give you RNH3 positive chlorine, a chloride ion, or you can simply say RNH3 positive and the sulfate ion. Okay, we should have these type of compounds possible with us, and what we are getting as a result, what is coming out as a result from here, H positive chloride and sulfates are moving towards the anion exchange resin. Chloride and sulfates are used with the anion exchange resin. So here H positive is coming, there we have release of the OH negative, there we have a release of the OH negative. So this H positive and this OH negative combines to give you water, which is considered as the pure water. Not pure, we are not talking about the pure terms, we are talking about the soft water. This water will be now considered as the soft. Now if you want to reuse this respective resin, the cation exchange resin, what you do, you react this RCO whole twice M with an acid. Maybe HCl you can use, maybe H2SO4 you can use. So what they will do, they will create this RCOOH plus maybe MCl or maybe MSO4. So you will be able to use again your cation exchange resin, and even what you can do is RNH3 positive Cl negative, react this with any of the base, let's say NaOH, and you are going to get RNH3 positive OH negative reacting with this to form your anion exchange resin. So you can produce, you can reuse it, you can reuse this. If you are able to produce it again, you can reuse it. Okay, so this is the synthetic resin method. This is considered to be the more superior method. It is considered to be superior of all of the methods present in the permanent hardness of the water. So please go through it very nicely. We have a diagrammatical representation in the package, your books, your targets, wherever you are studying, but the summary of this will be like this. Okay, now you can remove the hardness of water, you can remove the temporary hardness of water, you can remove the permanent hardness of water, but how to express that? If you want to know in terms of the numbers, what is the degree of hardness, what is that value, what is that number which tells you that yes, this number of hardness is present in the water. So now we have to calculate the, now we will do the calculation of hardness of water. Now we have to do the calculation of hardness of water. Okay, now understand one thing, that hardness of water is first calculated in terms of the unit, which is ppm, parts per million, and it is expressed in terms of a compound which is known as calcium carbonate. It is expressed in terms of a compound called as calcium carbonate. It is expressed in ppm, which is called as parts per million. It is expressed in terms of ppm, which is called as the parts per million, and it is expressed in terms of calcium carbonate. So how do you calculate hardness? So you take weight of calcium carbonate, you take weight of water, and you multiply that with the 10 to the power 6, and you get your hardness in the numbers. Now it's okay. This weight of water will be given in the question. This weight of calcium carbonate you need to calculate. Now how you will calculate? See, for that we have to use the law of chemical equivalence. For that we have to use the law of chemical equivalence, and that tells us that gram equivalence of calcium carbonate you have to take on the left hand side. Now what all salts are present which are responsible for the hardness of water? So we will take the sum of the gram equivalence of calcium chloride plus gram equivalence of magnesium chlorides plus gram equivalence of calcium sulfate plus gram equivalence of magnesium sulfate. Okay, so this is how you have to express. From this itself you can calculate the weight of the calcium carbonate. How? We can say that gram equivalence of calcium carbonate is equal to weight of calcium carbonate divided by its equivalent weight. Okay, we can have weight of calcium chloride divided by equivalent weight of calcium chloride. We can have weight of magnesium chloride divided by equivalent weight of the magnesium chloride. We can have the weight of the calcium sulfate. We can have the weight of the calcium sulfate divided by the equivalent weight of the calcium sulfate. Then we can have the weight of magnesium sulfate divided by the equivalent weight of the magnesium sulfate. From here you will be able to calculate the weight of calcium carbonate, and the equivalent weight of calcium carbonate will be molar mass of calcium carbonate divided by 2, because the n factor for the salt is the either total positive charge or the total negative charge. So the molar mass of this is 100 divided by 2, so it is coming out to be 50. For all of the other you can calculate the equivalent mass with the help of this formula. Now let's move towards a question. The question we have is, find degree of hardness in 1 kilogram of the water. Okay, first of all, the weight of the water I told you is given in the question. Having 0.6 gram of the magnesium sulfate, even the weight of the magnesium, molar mass of the magnesium sulfate is also given as 120 gram per mole. Okay, so let's start. We have to express our hardness in terms of weight of calcium carbonate, weight of the water into 10 to the power 6. Now weight of calcium carbonate we don't know. Okay, weight of water is 1000 grams, so we can take it as 1 kilogram as 1000 gram and 10 to the power 6. So we are not having this weight. First we need to calculate this weight. How we will calculate? How we will calculate the weight? By using the Law of chemical equivalence. So the weight of calcium carbonate divided by 50 is equal to weight of magnesium sulfate divided by what is the molar mass, which is 120 and factor is 2. So weight divided by 50 and the weight of the magnesium sulfate is 0.6 gram divided by 60. Calculate this. Calculate this. Weight will be equal to 0.6 into 50 divided by what? Divided by 60. Divided by, it's not looking in a proper way, so I should write it as 60. So 60 over here, remove this decimal, put it this over here. So this is having as 10 and this is having as 2, so it is coming out to be 0.5. This weight is coming out to be 0.5 gram. Now what you have to do? Now you have to calculate the hardness. Okay, so hardness you can have over here, the hardness you can have over here 0.5 gram divided by 1000 gram into 10 to the power 6. So this you can cancel, this you can cancel as, here it is coming out to be 10 to the power 3. You can have 500 ppm as your degree of hardness of the water. So easy this question is, and these kinds of questions are only coming in the examination. This is also a previous year question. Okay, I have not written the year, but this is a previous year question only. Okay, this is how you have to express the degree of hardness. It's very easy. Most of the things are given in the question itself, like weight of the molar mass of the magnesium sulfate is given, right, and the weight of the water is given. So maximum things are already present in your question itself. Okay, now let's move forward. Now let's move forward towards the questions now. Now let's move forward towards the questions. The first question which is coming is the isotopes of the hydrogen, tritium and protium, deuterium and this. So answer will be, I think, third. We should not have any doubt in this. We have already discussed everything in this respective topic. The chemical nature of hydrogen peroxide is oxidizing agent, but not in the basic medium. Oxidizing in the reducing agent, oxidizing in no. Oxidizing and reducing agent in both acidic and basic medium. Yes, we can use them as oxidizing agent and the reducing agent in the both acidic medium also, in the basic medium also. We have done the reactions in the respective class today itself. The temporary hardness of water is due to the bicarbonates. So only one option is present. See, so easy questions are coming. Now we have the next question. NaH is an example of sodium hydride. You know that the S block elements, you know that when hydrogen combines with the S block elements, it forms the hydride which is known as the ionic hydride. It forms the hydride which is known as the ionic hydride, which is also called as the saline hydride, Okay, so remember this thing. The hardness of a water sample containing 10 to the power minus 3 m calcium sulfate is. So you have to express here the hardness again, no problem. Hardness, you know that it is expressed in terms of the weight of the calcium carbonate. We can have the weight of the water into 100. Okay, not 100, actually 10 to the power 6. Now we have to first calculate the weight of the calcium carbonate. Okay, and we are having the molarity of the calcium sulfate which is responsible for the hardness of this respective solution, water. So gram equivalence of calcium carbonate will be equal to gram equivalent of calcium sulfate. Now we can use one more formula for the gram equivalence, which is mole into n factor. You all know that gram equivalents are also expressed in terms of the mole into n factor. They are also expressed in terms of mole into n factor. So we can have mole into n factor for the case of the calcium carbonate, and we can have mole into n factor for the case of the calcium sulfate. We can have these two things. These two things. Now moles, we have to calculate n factor of calcium carbonate is 2. Moles here, 10 to the power minus 3 molar solution means 10 to the power minus 3 moles are present in the 1 liter of the solution. Okay. So moles will also be 10 to the power minus 3 into 2. So you can simply say that the moles of the calcium carbonate is coming out to be 10 to the power minus 3. Okay. So we can simply say that the weight of the calcium carbonate will be number of moles is the weight upon molar mass. So you will have number of moles into the molar mass. The number of moles is 10 to the power minus 3. Molar mass is 100. So it is coming out to be 10 to the power minus 1 gram, which is 0.1 gram. Okay. Now express your answer. Your hardness will be equal to 0.1 divided by, you are not having the weight of the water present over here, but you are having the molarity, which is telling you that number of moles present is 10 to the power minus 3, and the solution is having the volume equal to 1 liter. We can take it as 1000 gram. Okay, because the density of water, 1 liter will be equal to 1000 gram, because you know that the density we can take it as 1 gram per liter in this respective solution. Okay, so into 10 to the power 6, multiply all of the things, multiply all of the things, multiply all of the things present over here, 10 to the power 6. So we are having over here, cancel this as 10 to the power 3. So you have 100 ppm as your answer. 100 ppm will be the answer. I have just expressed this formula. I have just used this formula. If I am not knowing this formula, this question can become somehow very tricky also. For those who are not knowing the concepts, they should revise that with the help of the mole concept chapter. You should know the weight of the calcium carbonate. By any means you have to calculate that. I have calculated with the help of the formula moles into the n factor. I have put the moles, I have put the n factor. I am getting first the moles of the calcium carbonate, then I am getting the weight of the calcium carbonate as 10 to the power minus 1 gram. After that I am having my hardness, express 0.1 divided by 1000, because I am taking the volume as 1 liter. So the weight will be 1000 gram, because I am taking the density of 1 gram per liter. I am taking the density as 1 gram per liter. Okay, so you'll get your answer as 100 ppm. Okay. So you need to understand all of these things very, very nicely. Now, the correct statements regarding the hydrogen gas as a fuel. Hydrogen gas is used as a fuel, and it is a very good fuel. First of all, it produces very less pollutants as compared to the petrol. When you have a combustion of H2, you get only the water. There is no any byproduct formed which is carcinogenic to the environment, right? So it produces less pollutant than petrol. Very true. A cylinder, see, the intermolecular force of attraction between two hydrogen molecules is very, very less. In the states of matter, you see that Z is greater than 1. They have very less attractive forces present between them. So if you want to convert them into the liquefied form, see, whenever you're transferring something, when you're transporting the gas, you have to take that into the liquid form. For the liquid form, we have to apply very high pressure for the conversion of the H2 gas to the H2 liquid form. So very high pressure is used. So tanks are filled with the hydrogen gas in the liquefied form, and that they are having very high pressure for conversion of the hydrogen gas to the hydrogen liquid form. Okay, so if by any means that is exploded, the pressure is released, there will be a very massive explosion. So the transportation of the H2 gas is the limitations the people are facing right now, the scientists are facing right now, although it's a very good fuel. Okay, a cylinder of compressed dihydrogen weighs 30 times more than a petrol tank. 30 times. You can understand what is the difference. So this is correct. Dihydrogen is stored in the tanks of metal alloys like NaNi5. Yes, we have to use a substance like this respective compound, because hydrogen can react also. Okay. On combustion, values of energy released per gram of liquid dihydrogen. No. Energy produced with the combustion of hydrogen is more than petrol. So it is wrong. So the answer will be A, B and C. All of these are correct. Volume strength of 1 mH2O2. What do you understand by the volume strength? 1 m. No problem. See, you want to calculate the volume strength. Okay, so the strength. Okay, 1 m solution. Volume strength you need to calculate. So what we have over here is, we need to calculate the volume. See, we have a formula. molarity is equal to V by 11.2. You need to calculate this V. Molarity is given as 1 m, multiply that by 11.2, you will get your V, and V is coming out to be 11.2 liter. Okay, this is coming out to be 11.2. You can simply have 11.35 they have written, so you can have your nearest answer as 11.2. The volume strength of 1 m H2O2 solution is present over here. Answer will be nearest as 11.2. Now we have the strength of 11.2 volume solution of H2O2 will be. Okay, no problem. You have to calculate first the strength. And for the strength, you need to calculate molarity into the molecular weight. Molarity you don't know, molecular weight you know that 34. Now how to reach to molarity? You have a formula V by 11.2, put the values 11.2 divided by 11.2, you will get a 1 m solution. Put the value, strength is 1 into 34, this is 34, and if they are asking you to calculate the percentage strength, it will be 34 divided by 10, it will be coming out to be 3.4%. And what they are telling you, the strength, but actually they are asking you the percentage strength, so answer will be 34%. They are not, if the percentage is written, they have not written properly in the question. This is percentage strength they are asking. Okay, so you have to go through the question very nicely. Now, 100 ml of a water sample contains this much gram of the calcium bicarbonate responsible for the hardness and 0.73 gram responsible for the hardness. Okay, the hardness of this sample you have to express in terms of the calcium carbonate. So let's start. No problem. Hardness you have to express. You know that it will be expressed in the weight of the calcium carbonate divided by weight of water into 100. You have to express like this. Now, weight of calcium carbonate. Now, the weight of the calcium carbonate, you will calculate, this is written as 100, and here you will be having 10 to the power 6. 100 ml of water means 100 gram of the water. Okay. Now, gram equivalence of calcium carbonate now will be equal to the gram equivalence of magnesium bicarbonate. They will be equal to the gram equivalence of first calcium bicarbonate. First, you have to take the calcium bicarbonate, then you will take the gram equivalence of magnesium bicarbonate. So these two you have to take. Calcium bicarbonate you will take and the magnesium bicarbonate you will take. So you will have weight of calcium carbonate divided by 50, as the equivalent weight of the calcium carbonate is 50, 100 divided by 2. Then we have gram equivalence of calcium hydrogen carbonate. So we have to take the weight, that is equal to 0.81 divided by molar mass of the calcium hydrogen carbonate divided by 2 plus 0. I think 73, yes, magnesium hydrogen carbonate weight, molar mass divided by 2. Okay, now put all the values. Weight by 50, this is 0.81. What is the molar mass of calcium hydrogen carbonate? It is given as 162. It is given as 162 divided by 2 plus 0.73. It will be 146 divided by 2. So weight divided by 50, it is coming out to be 0.01, it is coming out to be 0.01, because when you will cut this, you will get the 81. Okay, so this will be cancelled, 0.01. So weight will be 50 into 0.02, that will be equal to 1 gram. That will be equal to 1 gram. Now, put the values. That will be equal to, this weight you have to put 1 gram. Okay, so the answer will be what? Answer will be 10 to the power 4 ppm. Answer will be 10 to the power 4 ppm. 1, 2, 3, 4. 10 to the power 4 ppm. 1 gram we are getting the weight. 10 to the power 6. 1 ppm we will get the answer. This is also a very easy question. You can simply solve by using this equation, that you are required to first understand that you have to put this. The number of water molecules associated The number of water molecules not coordinated to copper ion directly in copper sulfate. Only one, because one is through hydrogen bond and other is through coordinate bond. One is through hydrogen bond. Four are through coordinate bond. One is through hydrogen bond, not coordinated to copper ion directly in the copper sulfate dot 5H2O. Next, the metal that gives hydrogen gas upon treatment with both acids as well as base. So we have to see anyone which is forming the nature as amphoteric. Zinc, I have already told you in the periodicity chapter, that forms the oxides which is amphoteric oxide. It is forming an oxide which is considered as amphoteric oxide. Zinc oxide is considered as amphoteric oxide. So it reacts with both acids as well as the bases. Next we have the correct statements among A to D are: saline hydrides, which are the ionic hydrides, produce H2 gas when react with H2O. Very true. Let's say I take NaH, I react that with the water. I'm going to get a base first and then I'm going to get a hydrogen gas. So this respective statement is correct. Reaction of lithium aluminium hydride with BF3 leads to B2H6. So lithium aluminium hydrides when reacts with BF3, you are going to get B2H6 plus lithium fluoride plus AlF3. All these compounds you are going to get. So this respective statement is also correct. PH3 and CH4 are electron rich and electron precise hydrides. Very true. If you make the phosphine, it is having the product or the shape like this. If you have the methane, you are having the shape like this. So it is electron rich. Very true. Electron rich because it is having the lone pair of electron. This is electron rich because it is having the lone pair of electrons, whereas this is electron precise because it is having the desired number of electrons, which are 8 around itself. HF and methane are called as molecular. I think they will be called as molecular hydrides because we are studying this only. So methane is a molecular hydride and even this is also molecular hydride. So A, B, C and D, all of the answers are correct. All of the options are correct. Okay. The synonym for the water gas, we call it as a water gas, syn gas or the synthesis gas. So the answer will be syn gas. Okay. Okay, so we are done with all of the important questions, theories. I have covered every bit of the important thing related to the hydrogen, its compounds, its structures, its questions. So kindly go through all of the chapter very nicely, make notes, go through them, revise them. Inorganic is something which requires the multiple revision. I have already told you inorganic is something which is very easy, very scoring. Even you don't have to think, you don't have to apply any formula, you don't have to do any mechanism. Directly you are going to get the answer. Just 1 second. But if you are not knowing the answer, that 1 second, answer is coming in the 1 second. And if you are not knowing the answer, you will be like, what? I should have learned it. Maybe you have a confusion that yes, this is a molecular hydride or the ionic hydride, but that confusion will get your marks cut. Okay. So please go through the chapter very nicely, the periodicity, the bonding, the hydrogen. Next we are going to discuss the S block elements. Like this we will discuss with all of the important theories and the questions. Thank you so much for attending.